Okay, so good afternoon, everybody. Thank you so much for joining this event. This is a part of RIKEN AIP Achievement Report event. And the title of this workshop is Workshop on Trustable Data-Driven Science. So I'm the team director of Data-Driven Experimental Design team. And let me briefly talk about the topic, that theme of this workshop. So let me start from a very brief introduction of my team. And the mission of our team is to developing machine learning methods and theories for AI-driven or data-driven science. And we have a lot of machine learning studies, developing algorithm, analyzing the property of the algorithm, etc. And at the same time, applying these methods to many scientific problems, including biomedical field and the material science field. And we have a lot of collaborators with the biological field and the material science field. So let me talk about the situation in AI for science. Now, in every part of the scientific activity, AI plays some important part. For example, if we think about the science as in this way, so the researcher first think about some hypothesis about research target, then predict the performance of that research hypothesis, and conducting experiment, we verify whether that hypothesis is true or not, and from the experimental result, we get some knowledge. So science can be modeled as a conducting loop of these 4 steps. And for each part of this step in the scientific activity, AI can play a very important role. For example, generative AI can be used for developing assumption, hypothesis about research target, and predictive AI can be used for predicting performance. And in order to conduct experiments effectively, we can use some iterative AI, such as Bayesian optimization. And after we get a huge number of research experimental results, we can analyze the results by using explainable AI, and that can, by that we can obtain some knowledge about the target. So it is very important to think about how we can use AI for scientific research. So our team has been interested in many things about AI for science. For example, how can we use AI and machine learning for generating scientific hypotheses? And the topic includes generative models for molecules and proteins. And the second topic is how can we use AI and machine learning for designing automatic scientific experiments. So that topic includes Bayesian optimization and experimental design. And the third topic, this is the main topic of this workshop, is that how can we ensure the reproducibility of AI or data-driven scientific finding. So that topic includes selective inference and conformal prediction. And in this workshop, we focus on the third one, how we can ensure the reproducibility and reliability of scientific finding, and some focus on selective inference. Actually, today, we have 5 talks, and among those, 4 talks are about selective inference. So what is the reproducibility in AI for science? This is just a simple illustration in the medical domain. So using so in the medical field, we can obtain a lot of data, like diagnostic data, examination data, genetic data, etc. Then we can use a variety of AI, and we will be able to do some prediction and getting knowledge or explanation. But since AI is very, very complex and it is data dependent, we have to guarantee the reproducibility. So here, in order to discuss that kind of topic, we are going to organize this workshop. And first, I'm going to talk about the basics of selective inference and what we are doing in our team. And from the second to his talk. They are invited talks. And second talk, Ronan will talk about some selective inference topic. And in the talk 3, Professor Imaizumi will talk about statistical inference for neural network. And in the talk 4, Yui, he was previous member of our team, is going to talk about selective inference after transfer learning. Then Yoshiyuki Ninomiya, Professor Ninomiya in ISM will also talk about selective inference. He will be coming to this site, not now, but later. Okay, so this is my introduction. All right, so let me talk about selective inference on complex machine learning models. And this is a joint work with our team members and also students in Nagoya University and Nagoya Institute of Technology. And I would like to thank all of these students and team members. And today I'm going to talk about selective inference for neural networks and selective inference for data analysis pipeline. And those topics are co-authored by the students listed here. And many of these students are already here. Thank you so much for coming and joining. Okay, so this is the picture I showed in the previous slide. So we are basically interested in reproducibility in AI for science. So in the scientific field, we can obtain a variety of data, and then we can use predictive AI to predict some, for example, the outcome of some examination, or using generative AI in order to get some knowledge about the medical situation, and explainable AI can be used for explaining what gene affects what type of phenomenon, for example. And those prediction knowledge explanation are very, very useful for medical treatment, for example. But since medical decision-making is a very important decision, we need to, guarantee their reliability. So especially we are interested in the reproducibility because they are scientific research. So here in the selective inference, that is the main topic of my talk and some other talk, we are interested in quantifying the statistical significance of the predicted result, or statistical significance of knowledge, statistical significance of explanation in the form of p-value. So as you know, in the scientific domain, p-value has been a very standard way to quantify the reliability of the finding. So therefore, we want to quantify those kind of reliability using p-value, even if they are given by AI or data. Okay, so let me start from a metaphor. So now, scientific finding is something like this. So for example, we have garbage, and within the garbage, a diamond, a treasure is hidden. So using some advanced AI tool, such as deep learning model, we would like to identify this diamond. So this can be interpreted as a metaphor of scientific finding from a huge amount of data. This is what we want to do. But since in the bottom, since AI is too powerful, even from the garbage only case, without any treasure, we might be able to find something look like diamond. So it looks like diamond, but this is just a result from the garbage. So this is not what we want to do in the scientific study, because in the scientific study, we want to find the true finding, not the false finding. So this means that AI is so powerful to find something from nothing. So this is somehow related to the notion of hallucination. So we need to be able to say that whether the finding we obtained from the AI is this true finding or false finding in a quantitative and general manner. So this is an important thing. So there are many types of approach for answering this kind of question, but we focus on so-called selective inference. So before talking about the selective inference, let's review the traditional statistical test and p-value. So as you can find in the standard statistics textbook, p-value is defined as shown here. So this is the distribution called null distribution. This is what we expect to observe from the normal situation. And this is our observation. And the p-value is the number that quantifies the statistical significance, how we are surprised with the observation. So it is defined by the tail probability shown in the red here. So this is what we have been using for quantifying the statistical significance of the scientific finding. So p-value can be simply defined by this equation. So probability of finding more extreme value than the observed finding. So this is the traditional p-value. But since if we use AI to find some hypothesis, then we are using data itself. So therefore, traditional statistical testing is not really appropriate. So what we need to answer is that how surprising is the finding, given that it is generated by AI. So we need to quantify this in the kind of p-value. And actually, selective inference provides that kind of p-value called selective p-value. Now, selective p-value is defined as shown here. So this is obtained based on the truncated distribution. Here, I will explain the meaning of truncation later, but roughly speaking, so since we need to say that given that it is generated by AI, we are conditioning on the fact that something was generated by AI, and the conditional probability can be used for quantifying the p-value, selective p-value. And the selective p-value is defined by this kind of conditional distribution. So this part is the same as the traditional p-value, but we have the conditioning part. Conditioning part tells that using data and then providing some AI algorithm to the data, then we identify that observation. So by conditioning of this, we quantify how surprising our finding would be. So this is the selective p-value. So if we can compute this selective p-value, even when some finding is obtained based on the data and based on the AI, we can somehow properly quantify the statistical significance. This is the basic notion of selective inference. So yeah, like selective inference, we're gonna use this kind of conditional probability. So now, let me talk about, briefly talk about selective inference literature. So I would say that the study of, precisely speaking, this type of selective inference is called conditional selective inference. There are many other types of selective inference, but conditional selective inference gained attention in the context of statistical inference for selected feature using Lasso. That paper was published in Analysis of Statistics in 2016. And around that time, many people started to focus, pay attention to conditional selective inference. So initially, selective inference was mainly considered in the context of feature selection problem, but it has since been applied to a wide range of problems. For example, in the lab of University of Washington that Ronan is from, they have application to clustering of selective inference application to clustering problem, for example, or change point detection problem, for example. So the technical challenge of selective inference lies in characterizing and computing the conditional distribution given the hypothesis selection. As I told you, selective p-value is just simply obtained by this conditional distribution. What we need to do is just computing this conditional distribution. But actually computing this conditional p-value itself is sometimes challenging if the AI algorithm is very, very complicated, such as neural network. So our main focus is to develop computational methods for conducting selective inference on complex machine learning models, such as deep learning models. Okay, so this is the outline of the rest of my talk. So I'm going to talk about three things: part 1, part 2, part 3. So part 1 is just a brief introduction to selective inference. And part 2, selective inference for deep learning models. And part 3, selective inference for data analysis pipeline. Okay, so part 1. So this is an introduction to selective inference with its application to lasso. Right, so let's think about the problem setting. So for example, select a subset of 10,000 genes, which is useful for predicting drug effects by using lasso. So we have gene 1 to gene 10,000. And from that, using feature selection algorithm, such as lasso, we want to select important genes. For example, this indicates that the gene 2, gene 5, gene 7 are selected. And then we can think about some prediction model using those selected genes. So the model for prediction could be something like this. And now we are interested in whether the second gene is really useful for prediction. We want to test whether this beta 2 coefficient for the second gene to be statistically significant. So which means that we test whether beta 2 is 0 or not, or beta 5 is 0 or not, beta 7 is 0 or not. So now traditional p-value, we can call it naive p-value, can be defined just by this. So this is observation, and this is random variable obtained from null distribution. If we compute this probability, then this is a p-value. But since we select the gene 2, gene 5, and gene 7 by using data, so it's a bias. So therefore, we have to explain the fact that they are selected based on the data. So therefore, selective p-value is appropriate for quantifying this. So by conditioning on the fact that those features are selected, gene 2, gene 5, gene 7 are selected, then we compute the probability of observing test statistics, which is greater than our observation. This is the definition of p-value. So the actual issue that we need to solve is how we can compute this conditional probability. So conditional probability computation can look like this. So I haven't mentioned this z capital Y equals z lowercase y. So this is a kind of nuisance component. So I'm not going to talk about the detail about this, but roughly means that we are interested in one direction of the test statistic. And for the other orthogonal direction, we are not interested in. So therefore, we can also condition on the sufficient statistics of this nuisance component. So this means that we can focus on a one-dimensional line in the data space. So this is a data space, and this is a test statistic direction that we are interested in. And then we can think about distribution, null distribution on that line. So this is our observation. So a point here indicates the data y, and then applying lasso, this indicates that lasso provide feature 2, 5, 7 are selected. And but if we, so this is the traditional p-value. But when we think about applying another data to lasso, then for example, if we apply data around here, then feature 1 to 7 might be selected. If we apply lasso in the data around here, 2, 7 might be selected, something like that. So now what the selective inference does is focusing on the case where 2, 5, 7 are selected. So this means that in this orange region, although the data itself are different from what we observed, 2, 5, 7 are selected. So selective p-value is defined under the condition that 2, 5, 7 are selected. So the same under the condition that same selected hypothesis, we can compute a selective p-value like this. So that means that we will need to identify these orange regions effectively. So this is the key point of the selective p-value computation. So this is a last problem, relatively simple. So we will be able to identify this orange region effectively. But for example, if we think about more complex machine learning model, such as deep learning model, how we can compute this orange part. So this is the main, problem that we have been working on. So this is the difference between the naive p-value and the selective p-value. Okay, so let me talk more about the computation of this selective p-value. Actually, in order to compute the selective p-value, we will need to solve an inverse problem. Inverse problem here means that we are interested in the data that result in the selection of 2, 5, 7. It's called like inverse problem. So solving this inverse problem is sometimes challenging. But since we can focus on a line in the data space, we have some way to solve this. Okay, so now let's move on to the second part, selective inference for deep learning model. When the model becomes complicated, such as deep learning model, how we can compute a selective p-value? That means that how we can identify the orange region. So now let me start from problem setting. There are a variety of problem setting about how we can use deep neural network for AI for science and what kind of tests we should do. But this is just an example. So let's think about the using a deep learning model for finding attention region of an image. So this is a brain image, and we want to identify which region we should pay attention to, for example, for diagnosis. And let's say we have the trained deep neural network, and providing this medical image to this trained neural network, it will be able to find some attention region. So there are many ways to do this. For example, CAM or GLAD-CAM, those kind of things can be used for spotting the attention region. Also, we can look at the attention value of the, let's say, transformer type model in order to find the where to look at. So anyway, many type of neural network can now provide this kind of attention region. But the question we want to answer is that whether, like how much we can trust this attention region, because they are like dependent on the data. And we want to quantify this by using p-value. So this is the situation where we actually have the region that we should pay attention to. But for example, when we provide this kind of lower image to the neural network, here this is a normal data. So this means that we don't really have to pay attention to anywhere. But since neural network is trained very well, so therefore it will be able to find some region that might be important. So in that case, we want to tell that this is not like statistically significant. But if we use traditional p-value, in both cases, the p-value becomes very, very small. For example, in this case, both of the p-value are 0.000, means that it is highly statistically significant. So in the upper case, this is fine. This is statistically significant. But in the lower case, we want to identify that this is just an artifact from the noise. But if we use naive p-value, the p-value was 0.000. So this is a false positive finding. But if we use selective inference, that means that if we condition on the fact that these regions are identified by using a trained neural network, we can compute proper p-value, selective p-value. For example, in the upper case, selective p-value is still 0.000, meaning that this region is statistically significant. But in the lower image, the selective p-value was 0.604, meaning that this is not statistically significant. If we consider the fact that these regions are identified by neural network. So there are several options for testing attention regions. For example, we can use anomaly detection algorithm, or we can use saliency map, such as CAM or GradCAM, or we can apply the segmentation. Actually, we have been working all of those situations, and some of the main authors are here. Like, for example, segmentation has been developed by Yui-kun over there, and the saliency map have been developed also by Yui-kun and other students, and anomaly detection have been studied in Shiraishi-san, Katsuoka-san, or some other students. But today, I'm going to explain anomaly detection case. And also another question is that how can we test the significance of the detected anomaly region? There are many possible ways to do that, but we focus on difference between the anomaly regions and the other region for simplicity. So let me talk about Katsuoka-san's work over there. So we use diffusion model for identifying anomaly region. So this is a standard diffusion model. So this diffusion model is trained to generate normal image. So in other words, we trained this diffusion model only with normal brain image. So therefore, if we input this kind of image that possibly contained a tumor lesion, generated image would be something like this, the normal counterpart of the input image. So it is very common that by comparing this input image and constructed normal image can be compared, and by taking the difference, we can identify the anomaly region. This is a very common way to do anomaly detection, or more specifically, it is called anomaly localization. So this is many people are working on, not we are working on especially, but we just think about this setting. So for example, these are the result of the reconstruction by using the diffusion model for a normal image in the left and tumor image for in the right. So we can identify some attention region properly in the tumor case, but we can also see that some noise can be identified also in the normal images. So this is a formulation about statistical test. We want to test the difference of pixel values between anomaly region and the background. So we just think about testing the mean of the detected region and the other region are statistically significant or not. So I'm not going to talk about a detailed technical thing, but we can think about some statistical model about the data and formulate a statistical test, like null hypothesis, alternative hypothesis, and test statistic. Then we can think about computing selective p-value. Again, this is a naive p-value without considering the fact that they are identified by neural network. On the other hand, the selective p-value are defined by conditional probability. Probability of observing more extreme value than the observation under the condition that those findings are identified by neural network. So the computation step is something like this. As I told you, the problem of computing selective p-value can be interpreted as a line search problem. So for example, if we think about image along this line, it looks something like this. And this is what we observed. Let me enlarge it. So this is our observation. But if we think about other images in that direction, we can think about this kind of thing. You can see that this anomaly region can be more clear if we go that direction. So since that naive p-value can be defined like this, On the other hand, a selective p-value can be defined under the condition that same region are selected as an anomaly region. So therefore, the selective p-value is defined like this, which is same as the case of the feature selection problem by using lasso. So this is the the left is traditional p-value and the right is selective p-value. So if the hypothesis is selected based on the data, this naive p-value are somewhat biased. So therefore, but if we use the selective p-value, we can properly quantify the statistical significance of the finding. So this is a result for of applying selective inference to the normal image. So the left part indicates a naive normal image, naive brain image, and the right part indicates the anomaly brain image. So if we look at the anomaly brain image where tumor lesion exists, both of the naive p-value and selective p-value are very small, like 0.000, 0.0332, 0.001. So this is fine because we can successfully identify some important lesion in the anomaly brain image. The problem is in the normal case. So if we compute a naive p-value, this is 0.027, 0.028, 0.000. For example, if we set the significance level to be 0.05, all these are considered to be statistically significant. But as you can see in this example, this is just an artifact from the noise. So but on the other hand, if we look at the selective p-value, this is 0.866, 0.611, 0.530, you can see that they are considered to be not statistically significant in the selective p-value. So this means that if we consider the fact that these anomaly regions are identified by using some neural network, then we can properly quantify the statistical significance. Again, so the issue is computation of the conditional distribution. And we have developed some trick to compute this piecewise linear decomposition of neural network. So for example, if we think about a simple CNN type neural network, the operation can be decomposed into piecewise linear function. For example, convolution is a linear operation. And if we use the ReLU activation function, this is by definition piecewise linear function. And max pooling is also identified, represented by a set of piecewise linear function. And thresholding is, of course, can be represented by piecewise linear function. And even if we think about some nonlinear transformation, for example, sigmoid function, if we can use sufficiently good piecewise linear approximation, we can put it into this framework. So anyway, by decomposing all the operation in the neural network to piecewise linear operation, we can do things. We can compute this probability. So it looks something like this. In the convolution and ReLU operation, we can identify the region by this way, and by max pooling operation, we can further condition on this, and by thresholding operation, we can further condition on this. So finally, we can obtain the region in which the same hypothesis will be generated by using the same neural network. And another trick, this is an implementation trick, is auto-conditioning. This is actually very, very important for practical usage of selective inference in complex machine learning models such as a neural network. So first, actually, this was an experiment by Nguyen over there. So when we first try to do the selective inference for a neural network, we have to implement everything for each component of the neural network. That was very, very tough work. And if we want to change slightly about the structure of the neural network, we have to re-implement again. This is not what we want. But fortunately, we can modularize the computation of each computation of the neural network and its associated selection event. So if we think about this modular case, we can just combining modular case. Then the selective p-value computation, the conditioning computation can be done automatically. This is this is what we call auto-conditioning, and this is in concept similar to auto-differentiation. Since neural network, for each component of the neural network, each layer of the neural network is constructed in a modular way along with the back propagation computation. So therefore, just by putting layer by layer, then back propagation computation for training can be automatically done. We can do the same thing for selective inference. And actually, Katsuoka-san over there developed very nice software called Selective Inference for Onyx. As long as a trained neural network has been saved in the format of Onyx, for example, you can use PyTorch or TensorFlow, most of the framework, deep learning framework, we can represent this by Onyx format. And then we can conduct selective inference without additional implementation by using the notion of this auto-conditioning. So if you are interested in this, you can ask Katsuoka-san later. And this is a demo. Since I don't really have time, I cannot explain the detail, but this is just a simple notebook for demonstrating how we can use SI for Onyx. So let me skip this. And actually, we just have that conventional way of writing code for the neural network. And maybe it's difficult to control the video, sorry. Yeah, just by writing this amount, then we can conduct selective inference for on the trained neural network. So what I just want to say that you don't have to do something extra for conducting selective inference. What you need to have is you need to have a trained neural network and the proper definition of the statistical test. Then implementing just in this kind of amount, then you can conduct selective inference. Okay, so let me briefly talk about the selective inference for data analysis pipeline. So as you know, so data analysis is very, very complicated, starting from data collection, data processing, learning and evaluation, analysis and discovery. So many steps we need to consider. And the important point that depending on the researcher, depending on the task, the pipeline for data analysis can be different. For example, the first researcher has this pipeline, and the second researcher has another pipeline, and the third researcher has another pipeline for their own purposes. But we wanted to provide a way to quantify the statistical significance of these findings after these pipelines. So, but if there are a lot of, selective inference professionals in the world, then each professional can help them to compute the selective p-value. But unfortunately, no. So therefore, we want to, provide a way to compute the selective p-value for arbitrarily designed pipeline. So in order to do that, we need to provide some framework that just by describing the pipeline, then automatically selective inference should be possible. So this is what we really want to do. And actually, we are still in the starting point, and we have considered a very simple framework just for feature selection. That consists of missing value imputation, outlier removal, feature selection. But within this context, whatever pipeline user are interested in, we can provide a selective p-value of the finding obtained by this pipeline. So I'm not going to talk about the detail, but anyway, we can do that without any additional implementation. So this is a demo, but let me skip. Sorry. Yeah, so same problem. like under the condition that the same pipeline is selected, then we want to guarantee the statistical significance. This is like a selective p-value computation. And in order to do this, we actually do the same thing as SI for Onyx, auto conditioning. So for example, for each missing value imputation algorithm, for each outlier removal algorithm, and for each feature selection algorithm, we also develop associated selection event computation. So therefore, by combining these components, by developing any pipelines, we already know that how we can compute the selection event, how we can compute this kind of region. So this is same as the auto conditioning SI for Onyx. And actually, this is the code written by Shiraishi-san over there. And just by writing this, this is just a pipeline. We first do this type of anomaly detection and this type of missing value imputation, and conduct this feature selection, something like this. Just by writing this, and without additional implementation, we can conduct the selective inference for this pipeline. So anyway, as I told you before, in the future, we'd like to go to this direction. So whatever the researcher develop the pipeline for their own data analysis, we want to compute the selective p-value. By doing this, AI-driven science, data-driven science can be more trustable because we can properly explain the fact that how the data or how the AI algorithm affect to the result properly. This is our next target. And since this is our, progress report presentation, so let me show you the list of our selective inference work in the past 10 years. So 10 years is the period that this RIKEN team has been developed. So we started, our first paper on selective inference was published in 2017, ICML. So fortunately, every year we have at least one publication. So now, 2025, and today, acceptance letter from the new LIPS have arrived for Nihori-san's paper over there. He's now sleeping, but anyway. Okay, so thank you so much for, yeah, this is the end of my talk. Thank you so much.
Okay, yes. My question is about test statistic direction. How we define that direction?
Okay, so let me provide an example in the case of feature selection. So now we are interested in test whether this linear model coefficient is 0 or not. So if you are familiar with least square linear regression, this beta 2, sorry for the small display, but X transpose X inverse X transpose Y, right? So this is our interest. So now this, as you can see, this is Y, this is -1, but anyway, this is a linear function with respect to Y. So therefore, this could be the line of our interest. So if you are interested in testing the beta 2, then we have this line. If we are interested, if you are interested in testing beta 5, you have another line or something like that. And also for the other problem, like medical image, we can define similarly.
Let's say we have an interest in beta 1, beta 2, and beta 3. We have 3 lines. Do we somehow interested in jointly looking at their intersections?
Yeah, that's a very important question. It's a kind of like multiple testing problem, like simultaneous confidence interval or something like that. Yeah, so if we think about those kind of problem, we need to think about more like a complicated subspace. But for example, if you are interested in like multiple testing, you do each selective p-value, and just for example, applying traditional multiple testing collection like Bonferroni collection would satisfy things. Yeah, but that's a very good question. Thank you so much.
Thank you.
So.
Okay, so it's almost time, so we want to move to the next speaker.
Okay,
Thank
thank you
you.
so much.
So as was mentioned, my name is Ronan, and I'm here from the University of Washington, the Department of Statistics, where I'm advised by Daniela Witten, and our group broadly focuses on a variety of problems in the field of selective inference, but I'm going to be talking about some current and ongoing work that we've titled Post-Selection Inference with Penalized M-estimators via Score Thinning. So I'll get into what some of this means, but luckily we've had a great introduction to selective inference in certain topics like the lasso and feature selection, and that will do well for us here. So I'm going to open with kind of an outline. So I'm going to start with a motivating example, and we're going to be considering inference on the lasso there. And so we've already kind of seen a little bit of what that problem is, and then I'll go into the background of what penalized M-estimators are and what it means for a confidence interval to be valid in the selective sense. Then I'm going to talk a little bit about the underlying theory coming from the statistics department. That's part of what we value there, and some of the properties, and then 2 ways to achieve valid inference after selection. And we'll conclude with a little bit of a simulation study. So to start with, we're going to consider sort of this motivating example that's very popular and common in the field, that is inference after the lasso. So we're going to use this lasso, this is an L1 penalized linear model, to select a sparse model. So these are features that are going to be of interest, and that's step 1. And since I'm in the stats department, we like using R, but you can run this using scikit-learn too, or similar stats packages in Python. You can just run lasso out of the box and select the non-zero coefficients. That's going to be your selected model. Now, what if we want to conduct inference in this model? As was described before, what if we want to know if a selected coefficient is actually statistically significant? Well, we can run an ordinary least squares model, for instance, and generate confidence intervals. So that's inference, and that's step 2. So selection is step 1, inference is step 2. And again, we're going to use an out-of-the-box tool in R. And the problem is, just if you run this quickly, you'll get under coverage. So in this case, I got coverage was 80%, but I want it to be the nominal level 95%. And so what's the problem here? Well, the problem is that we double dipped. So our model in step 2 was selected using the same data as was used in step 1. So we're using the same information twice. And so we shouldn't be surprised that features that were selected in part 1 because they were, say, high correlation with the outcome, were then shown in step 2 to have high correlation with the outcome. So double dipping broadly, and I'll just kind of go through this, is an area of interest in multiple ways. So selection can be not just feature selection, but hyperparameter tuning, risk minimization, early stopping, clustering, outlier detection, change point detection. These are all problems of interest. And then inference, maybe we're interested in generalization error or confidence intervals, p-values, goodness of fit, all sorts of inference estimators are of interest here. And for the purpose of this talk, I'm going to be specifically talking about confidence intervals after feature selection, but we're hoping to generalize it to some of these other problems. And the common problem across all of these is that we're using the same data for selection as we use for inference, and that leads to invalid inference guarantees. So most inference guarantees rely that the model is fixed, but if we do some sort of selection procedure beforehand, we get into trouble. So a common solution that many people here are probably familiar with is sample splitting. And this sample splitting just splits the data into 2 independent pieces. So we can consider here we have 5 samples, Y, and we're just going to split it into 2 pieces. And these pieces are independent. And so we can use Y1 for selection and Y2 for inference. And because the pieces are independent, inference and selection are independent, and therefore all inferential guarantees are valid. And so sample splitting is a great solution when it works. And one fantastic aspect of sample splitting is that we don't need any new methods, right? You can use whatever methods you are already familiar with. You can do model selection, then inference, and everything works. But there are some limitations of sample splitting. And so first of all, it's not necessarily applicable to non-IID data, independent and identically distributed data. So if you have spatial data, time series, data that lives on a network or a graph, or fixed X regression, you might not want to do sample splitting, or you might not be able to do sample splitting in a way that makes sense. It's also not applicable when selection depends on the sample size. So for in clustering, you care about what the sample size is because each point gets put into its own cluster, and so it doesn't make sense to do sample splitting in that setting. And it can also be sensitive to outliers depending on how you split the data, especially at low sample sizes. And so one solution that's emerged in the past couple of years is called data thinning. And in particular, I'm going to talk about data thinning when the data is Gaussian, or Gaussian data thinning. So in our case for regression, we're going to suppose X, our covariates, are fixed, and our outcomes, imagine they were Gaussian. Well, then we can choose this tuning parameter gamma and sample some additional random noise. And then we can construct two new pieces of data, y1 and y2, by adding and subtracting this sampled noise W. Well, why are we doing this? Well, the answer is that our resulting y1 and y2 are now normally distributed, and more importantly, they're independent. And so just like sample splitting, we can then use selection using y1, and that will be independent of the inference using y2. And so our inference is valid, and we're not going to double dip. And there's a lot of lines and work on using this. And it's importantly applicable to non-IID data and when the selection depends on n. So in some of these problems like clustering, fixed X regression, spatial data, this is a solution that works when sample splitting fails. And what does it kind of look like visually, if that helps? So we have our same samples as before, but this time we're going to split it into two pieces of equal size, but they're slightly noisy. Instead of the same values as we would observe with sample splitting, here you sort of get noisy versions of the original data. So you add some noise. Sample splitting adds noise by reducing your sample size. Here we add noise by corrupting sort of the data that we have. And then selection and inference proceed as before. And just like sample splitting, it's great because the pieces are independent and you can use whatever procedures you want. And so we can sort of take this back to our lasso example. So if X is fixed, this is a fixed X setting where we don't want to do sample splitting. And suppose Y is Gaussian, which is a strong assumption, but we can construct Y1 and Y2 using our data thinning. Then we can use the lasso to select a sparse model on Y1. And all I've changed here from my pipeline before is I've sampled W and I've added it to my outcome. So I'm fitting a lasso to slightly noisier data. It's not sample splitting. Here instead we're noising our outcomes. And then I can generate confidence intervals from an ordinary least squares model like before on Y2. And here all I'm changing about what I did before is that box in orange, I'm subtracting noise. So I've added noise in the selection step. I've subtracted this noise in the inference step. And coverage is 95% or about. And so this works. This is great, as we expected, right? Our data is Gaussian. And so this creates independence. Okay. But it's also a solution for non-Gaussian outcomes in this setting. So if X is fixed and Y is not Gaussian, I can construct Y1 and Y2 pretending they were Gaussian, but we know they're not independent because our assumption of Gaussianity of the outcome does not hold. And then I'm just going to do what I did before. Same exact thing. I'm going to fit a lasso to the noisy outcomes, even if the outcomes aren't originally Gaussian. Then I'm going to generate confidence intervals, and coverage is 94%. So coverage is still quite high. It's approximately works. Why does it still seem to work in this case, even when our theory doesn't hold? And so there's some existing work on this area, and there's a couple papers of note. And the first one is one of the papers that pioneered data thinning, and they said, well, what happens if we don't actually have Gaussian data? And so they go into a very specific case. They say, what if we have selection is a convex constraint on Y1? So what if it puts Y1 into sort of a polyhedron, for example, the lasso, or many of the works you've seen before here? Then inference is just specifically the mean of Y. So you're interested in, say, the coefficient or the, what the mean of Y is to some extent. And this is an example of this would be ordinary least squares, where you're sort of choosing a contrast with the outcome of Y. And they showed that this is asymptotically valid under some conditions, some sort of new conditions. There's also this other work by Li Hua Lei, and they say, well, and their theory works when selection is any function not of a convex constraint, but just any function generally of X transpose Y1, so this noisy data. And then once again, inference on the expectation or contrast of the expectation of Y, and they have a couple other conditions here. So this has been, to some extent, addressed in the literature. But does this work for not just ordinary least squares? Does it work for other models? And to some extent, yes, it does. So suppose that instead of Y, it's not even continuous, it's discrete, it's 0 or 1. We're doing, say, a classification task. And so in this case, we wouldn't use ordinary least squares. We would use logistic regression as a simpler case. So we can construct y1 and y2 as before. We're going to add Gaussian noise to our outcomes. Our outcomes are 0 and 1, and all of a sudden we've added Gaussian noise to them. Okay, it's sort of weird so far. But we're going to apply the same procedures before. We're going to select a sparse model on y1. So I'm now using logistic regression. I have binary outcomes, and I'm adding Gaussian noise. And I'm going to use the selected features, and I'm going to make a confidence interval using logistic regression, subtracting the noise this time. And coverage is 98%. Okay, so why does this still work again? So even now we've just kind of changed the problem. It's not even continuous. It's zeros and ones, and I'm adding noise. And one aspect of this is most, with the lasso, because it's mean squared error in continuous inputs, you can just add noise. In this case, we have to write, most logistic regression solvers require you to have binary or discrete outcomes. And in this case, you can still do the optimization procedure. You just have to write your own function, but it's pretty simple. And so why does this work for non-Gaussian data? Well, this is where our work kind of comes into play. So we're considering this set of penalized M-estimators. So for example, the lasso is one, but here we're just minimizing a loss function with some penalty, and I'll get into that, what exactly that means in a second. Then our inference is on any of these like population quantities. If we had infinite data, just the expectation minimizer, the population minimizer. And we require some conditions on rates or bounds on the selection probability, but then we're going to get a confidence interval that's valid conditional on the model that's selected. So this is exactly what we want in the selective inference framework. And so now we're going to get a little bit into the background, and it's going to get a little bit more statistical, a little more notation heavy, but then we'll sort of zoom out later on, and hopefully if I lose you a little bit in this section, we can bring you back in later on. So what is an M-estimator? So suppose we have independent data. It doesn't have to be ID. We need independence, at least in this case, X and Y. So this is just a classic regression setup. And we have a subset of the features E. So if there are 20 features, maybe our model is features 1, 2, and 4. We have a loss function that we're going to be minimizing, and then we might consider minimizing that loss function in the selected model. So if we zero out a bunch of the features and we only optimize over the features E. And then we have this sort of ideal minimizer. This is the population minimizer in expectation. So this is, ideally, this is what we want to minimize. This is the target. But we don't know the expectation because we don't know the distribution. So we're just doing empirical risk minimization. We're just minimizing the average loss in our selected model. And if we're working in a fixed model, statistics literature going back to the last century has really done most work on this. So we're doing inference on a parameter, the jth parameter, for instance, and we can just construct a classic 1 minus alpha confidence interval in M estimation. So we have some point estimate theta, we have a variance estimate sigma, and we're just doing theta plus or minus a z-score, maybe 1.96, depending on what your alpha level is for the confidence interval. And the confidence interval is valid, asymptotically at least, if we cover the true parameter at level 1 minus alpha in the limit. So this is classic, in ordinary least squares, this is very common, but for any sort of logistic regression, generalized linear model, much more complicated models, this has been explored. And so classic theory gives us valid point estimates and standard errors. So this is what I showed before. You just fit this in R, you get your confidence interval, 2 lines, this is valid. So now if we add a penalty to our M-estimator, then we are able to do model selection. So we can have any sort of non-convex sparsity-inducing penalty row, but you can just think of it as the L1 norm, and that would be the lasso. And so the penalized M-estimator is the same thing before. It's sort of the average loss, but we're adding this penalty. So this would be structural risk minimization if you're coming from the more machine learning background. And then because our penalty is non-convex and induces sparsity, we're going to, or at least non-differentiable is still convex, we're going to get some non-zero coordinates and some zero coordinates, and we're going to use that to select our model. So when we run the lasso, it's going to tell us that a subset of the features are important, and the rest it's going to zero out, and those are the features we want to do inference on. So now all of a sudden we've used the data to select our model. So this is a random model. And going back to the code, this is just, you run in R, you use the glmnet package, and you select some features that are non-zero, and this is exactly what I was doing before. But the problem is that the classic confidence interval isn't valid in a selective sense. So I've used all of the data y to compute the lasso estimates, the theta tilde with the lambda, and then also the regular estimates, and this is double dipping. So this is what I showed before. We're fitting the lasso on the data using the same data to run an ordinary least squares model, and it's not valid. So it's the coverage or the probability that the truth lies in our confidence interval, given the fact that we selected our model using the data, is less than 1 minus alpha. So it's less than the target level. That's not what we want. That we lose all statistical guarantees without additional assumptions. Instead, what we want is a valid selective confidence interval. So we want new estimators, and I haven't told you what these are exactly yet, although I've hinted at them, and we want them to provide valid selective coverage in the sense that the probability that the truth lies in the confidence interval, given the fact that I've selected the model using the data, is above 1 minus alpha. And so this is kind of what I showed before. It seems like we have a way to accomplish this. If we add Gaussian noise to our outcomes, even if they're not exactly Gaussian, we achieve this result. We have valid coverage. So this is our goal with our estimators. Okay. So how are we going to go about doing this? And I'm going to introduce an estimator and then talk about something that we call the core statistic. And this will probably be the most theoretically heavy section of the talk. So I'm going to introduce two noisy M-estimators. So I'm going to show what we had before. I'm just going to change them a bit. So we have some noise W. We've already sort of talked about this idea of adding random noise, sampling random noise, and then adding it to our outcomes for some covariance matrix sigma n that I haven't told you yet. And I'm going to define a new penalized M-estimator. And it looks the exact same before, but I've added this orange term. And this orange term is just a noisy affine penalty. So it's just kind of perturbing the objective function in some direction. And I'm going to define a new M-estimator for inference. This is the same thing before. We're minimizing the average loss in our selected model, but I'm subtracting this noisy penalty. So I've added a penalty to the selection and subtracted a penalty from the during inference. And now, why am I introducing this? Well, we're going to study their behavior. And so M-estimators are minimizers. And so when we think about minimization, we often are looking for zeros of the gradient. So we take a derivative and we set it to 0. That's often how we're solving a problem or studying their behavior. So M-estimators are going to minimize this function. So we care about the 0 of the gradient. And so since we can just take the gradient of the sum as the sum of the gradient, we have this derivative here. And if you care for the exact definition, we just, the derivative in this model, in this submodel for the features that we care about is just the derivative of each of those components evaluated, or each of the selected features evaluated at some theta. But we're just taking a derivative here. And so this term, this statistic, we're going to call the core statistic. It's going to kind of come out of nowhere at first, but it's the gradient evaluated at the population quantity. And it's normalized by this root n. So right, the M-estimator is solving for a 0 at the estimated quantity. Here I'm plugging in sort of the true quantity. So they have this z hat n. And I don't know what z hat n is because it's a function of theta star, but it's just an average of our loss at the truth over our samples. But we can relate any estimator via a Taylor expansion to z hat n. So z hat n is the first term in a Taylor expansion. And this is a pretty typical way to study the M-estimation problem. But if we do a Taylor expansion of our gradient at or around the truth, we end up with a series of terms. We end up with z hat is the first order term. We have this second order, or this, we have z hat n, then we have this other term, and then we have a remainder. And HE here is just a fixed matrix, and we have some random remainder that depends on higher order terms. Okay, so it's getting a little complicated so far, but if we, the theta, an estimator will solve for will minimize the gradient or minimize the objective function, so it solves for 0 of the gradient, and we can Taylor expand that gradient. And it seems that a lot of the randomness depends on z hat n. Now, in typical conditions, the remainder is vanishing. It's little op1, so it's going to converge to 0 in probability. So really, the bulk of the randomness that matters, the data only matters through the z hat n. And what's important is that z hat n, this core statistic, is approximately normal. So it doesn't matter what the data is, its average in this core statistic is approximately normal. So if I define sigma n to be the variance of z hat n, or the covariance, and then I define this truly random normal variable z to be mean 0 and have this covariance sigma n, then under some conditions, this is the theoretical result, but effectively z hat n is approximately normal. It looks a lot like zn. Okay. And why does it matter that this function of the data is approximately normal? Well, we know that we can thin something that's normal into independent pieces. So we know z hat n looks a lot like a normal random variable. And so we can take z hat n and we can split it into two pieces by adding and subtracting this noise. And we have a couple claims. And the first is that our proposed estimators that I showed implement this thinning, provide noise to this quantity. That z hat 1 and 2 are approximately normal and independent. So if z hat n is approximately normal, when we thin it, it's approximately normal and independent. And lastly, that we have some control over a conditional probability. And if we're thinking in the selective inference setting, this is because we want to do selection using z2 and then inference using z1. And so this conditional probability is important. And we'll kind of go through this. So we recall our penalized M-estimator. And so this is just the same thing, the typical thing we have in a regular setting, except we've added this noisy penalty. Okay. And so what does this do? Well, when I take the derivative of this objective function, because I'm going to solve for it being equal to 0, or at least 0 being in the subderivative in this case, but we don't need to get into that, the derivative of the noisy term, we're just going to drop that theta out. So all I'm doing is now I'm adding noise to my gradient. I'm adding this W, this scaled W noise to my gradient. And so when I recall that Taylor series from before, when I add that noise in the left-hand side, it should be actually plus a gamma, not minus 1 over gamma. But I get, we Taylor expand the gradient, and I end up with z hat n in the right side plus a gamma W. And we know that is z hat n1. So when I Taylor expand without this noisy penalty, I end up with z hat n. When I add this noisy penalty, that ends up in the derivative, or ends up in the gradient. And all of a sudden, I've kind of noised my gradient a little bit. So now the randomness in my gradient, which is being set to 0 and important for optimization, is now z hat n1. And if I do this with a similar Taylor expansion for the inference estimator, I'm going to get z hat n2, which is just subtracting this noise. Okay, so our estimators, by adding noise to the objective function, we add noise to the gradient, and this randomizes this function of the data. The second claim is that we have approximate normality. So now we've constructed this z hat n1, z hat n2, but now we're sort of claiming that they're approximately normal. So we recall we have this truly normal random variable zn, and we have some noise, and we can consider thinning zn with this noise. And we know that if we thin a normal random variable, it's independent and it's normal. And now what does this get us? Well, here's the formal statement, but informally, z hat 1, z hat 2 are approximately equal in distribution to zn1 and zn2. So they're approximately normal and independent. So if they were actually normal, they're exactly normal and independent. If they're approximately normal, now they kind of look like a normal random variable. So even though our data isn't normal, a function of it is close to normal, and we can thin something that is close to normal into things that look almost independent. And that gets us to sort of the final, most technical aspect of this before we kind of zoom out into maybe some more relevant stuff, is that if I have some sets and I have some vanishing remainders, under a couple conditions, I end up with a statement that effectively the conditional probability of z hat 2 given z hat 1 with up to some vanishing remainders is close to the unconditional probability zn2. And why am I even writing this? Why is this a punchline to some extent? Well, if step 2 our coverage event is something like the event that z hat 1 plus or z hat 2 plus its remainder is in this set. And similarly, step 1 is the selection event. Then we know that's it's close to event that we can control, or some Gaussian quantiles. So this is kind of, we've gotten to the meatiest complicated theory aspect of it. But if we can thin z hats into two pieces, then they're approximately independent, and they're approximately independent in the sense that we have some control over their conditional probabilities asymptotically. Okay. And so now what is this kind of, we've talked about this core statistic, we're going to thin it, and this is going to get us to two valid ways to do post-selection. Okay, so now we've had enough time to digest that final punchline. This is going to get us to some of the more maybe interesting aspects of what is the outcome of some of this theory regarding the core statistic. And so what we can show is that the event that we select these features E is the same thing as the event that z hat 1 plus a vanishing remainder is in a set AN. AN is a potentially complicated set of the union of many of convex sets, which we now have some software to characterize exactly in some problems, which is great, but we just know it exists in this setting. And then similarly, there's another set B, and the event that we cover the true parameter is equivalent to the event that z hat 2 plus a vanishing remainder lies in this union of convex sets Bn. So we've characterized what the selection and inference events are in a general form. We don't actually care what An or Bn is. We just care that they're unions of convex sets. And then by construction, this third term is just a Gaussian quantile. It's, you know, how we get asymptotic theory in general for confidence intervals. But what that gets us is then if I do selection and inference, I've decoupled this conditional probability. And this is sort of, we're reintroducing these estimators from before that I told you. But now we have kind of the final statement. That is, if I sample this noise and I add these penalties to my loss function, or to my loss functions, or effectively to the objective function, then I end up with asymptotically valid conditional selective inference, in the sense that the confidence interval from this ordinary least squares model with an it's not an ordinary least squares model, it's just any M estimator with this added penalty, that confidence interval covers the truth, conditional on the fact that we selected the data using this L1 penalized, or more generally, sparsity-inducing penalty term M estimator. So we have this probability event. So this is great, but if you remember, this isn't exactly what we were doing in the beginning, right? We were adding noise to the outcomes, and that gave us valid inference. So here we're adding noise to the objective function, but we have a second way to provide valid inference after selection, and that is if the xi in this regression sense are fixed, and the gradient is affine, or linear in some ways, in y, then instead we can sample noise on the scale of the variance of y. And we can just instead run our penalized regression using noisy outcomes, where we've added gamma times this noise. And then we can run inference using by subtracting this noise. And then once again, we end up with a similar valid coverage statement. So if this was Gaussian data thinning, this would be immediately apparent because y's become independent and it works. But here it works, as we've kind of seen, because under the hood, we end up with this asymptotically normal core statistic. And that gives us asymptotic independence of these two procedures. But how did we get from the noisy penalty to this noisy outcome setting? Well, it's actually pretty straightforward in the sense that, once again, we're requiring xi or covariates to be fixed. This is a setting where we don't want to do sample splitting. We maybe have some structure to xi that we've set up, and we have an affine gradient. And so if I take this gradient and I add noise, then I can, because it's affine in y, I can split it up into two pieces. And that first piece is exactly, that sum is what we defined our core statistic to be, this z hat n. And our second term is, by construction, normal 0 sigma n, because w's are exactly normal, and then sigma n is related to that derivative. And when you sum them together, you end up with z hat n1. And similarly, you would recover z hat n2 for the inference step where we're subtracting this noise. And when is this derivative affine in y? Not necessarily not all objective functions are. A loss like mean squared error is, but in generalized linear models, including logistic regression as well as ordinary least squares, it's affine in y. So that's a useful case where this is relevant. So, and for statisticians, they care about Poisson regression or logistic regression, among other forms. And so it's less general than the noisy penalty because we need the gradient of the loss to be affine, but it may be easier to estimate the variance of y than whatever sigma n is. And to a lot of us, it's more important because we can just use whatever existing software we want. I can use Lasso out of the box and then run an inference procedure like ordinary least squares. And lastly, just quickly, sort of we can see how this works in practice, or we're just going to simulate data from a sparse logistic regression model. Although I don't actually care what model we select. I don't care about selecting the true model as some theory cares about. And then we're just comparing classic inference to these two thinning approaches. And so we have coverage on the y-axis, and it should be 90% at the red dashed line. And I have sample size. And we see that the classic method is underperforming. It gets slightly better as the sample size increases. But in contrast, across all the sample sizes, both the thinning approaches work quite well. So even though our theory here is asymptotic, in practice, they also work quite well at low sample sizes. And in short, it's common for selection and inference to both be functions of a function of the data, in this case, the empirical loss, but we know that leads to double dipping. But empirical loss depends on the gradients, and even if the data isn't normal, the gradients may be approximately normal. And we know what we can do with approximately normal. We can thin it into items that look close to independent. And so we can add this noise to the gradient to decouple selection and inference. And in practice, this is done by a noisy affine penalty in the optimization strategy, but we can also add noise to the outcomes if the gradient is affine. And I just want to acknowledge the main two collaborators on this. So Daniela Witten, who's the PI and my advisor and leads the Selective Inference group at the University of Washington, as well as a collaborator of ours, Snigdha Panigrahi, and she's at the University of Michigan, but works a lot with randomized conditional selective inference. So thank you for listening, and I will take questions.
Yeah, thank you for the talk. So in general, I feel that there's some kind of like randomization. You add the noise to the original response vector. You add the noise to the loss function, and you add the noise to the gradient. But I feel that when you add the noise, you change the solution, right?
Yes.
Originally, you have the solution. But after you add the noise, you change the solution themselves. So I feel that it's kind of like changing the problem so that you have your purpose of like getting the valid confidence interval.
It's a trade-off of so just like sample size, or just by like sample splitting, you add some randomization, and it's going to change what model you select. And so there's a trade-off of here we add some noise, and you might lose some selection power. So maybe your model you might not think is as accurate. You might also consider it to be just a form of regularization. So there's actually some interesting work. Snigdha has a paper with decision trees. We're actually adding noise when fitting the trees leads to more predictive trees because it regularizes the model so it doesn't overfit to the data as much. So it's an interesting trade-off. But yeah, certainly you're incredibly correct that by adding noise, we've sort of degraded our model selection.
Yeah, but is there any like investigation whether you that investigation whether when you add the noise, how close the approximation to the original estimate?
So we aren't, studying how close it gets to the estimate. We know it degrades, right? So you're going to end up with a different model that you select. So this is different from, if an investigator comes to us and says, I selected this exact model and I care about this exact model, then we don't have, that's where we need to do exact conditional selective inference.
Okay,
but here, it's, we're kind of requiring that you select the model in a different way with some noise.
Okay, thanks. So I have the second question is that, so in the original problem, so we rely on the independent, like the test statistic is independent of the nuisance component. Therefore, we have the finally, when we compute the p-value, we have the truncated univariate Gaussian distribution. But in your case, when you add the noise, so I don't know how can you compute in your setting, whether it's the truncated Gaussian in the one dimension or in the high dimension.
So here you don't need to do, you're not changing the, there's no truncated Gaussian. Sort of, you just have an, you've added
okay.
noise and it's asymptotically Gaussian.
I
but
see.
it's
No, I understand. Okay, thank you very much. Okay, thank you very much.
Yeah, thank you so much. Very interesting. So I'd like to ask about the amount of noise that you would add. So I assume that in the case of very simple data thinning, you have already analyzed like how much noise you should put on. But in the case when you put the noise to the objective function, the control of the amount of noise seems to be a bit complicated to control. So like, can you say something about this?
Yeah, so if we go to, so if in the outcome setting, a typical
Maybe
thing.
that's more simple, right?
So this is the simplest one, and if you set gamma to 1, that is like doing sample splitting with 1/2 in each part. And so that trades off the amount of noise equally in the two. So that's kind of our default for this as well, as setting gamma to 1 in this penalty. Although you're right, it's a little bit less, what it's doing is it's doubling the variance of the core statistic. So if we know, selection and inference here are approximately just equal to the core statistic or a function of that z hat n. And so by adding with gamma being 1 here, you're just doubling the variance in each problem. So gamma equals 1 is like sample splitting with 1/2 sample size in each portion.
Yeah, but it depends also on what type of original loss function would be and what type of penalty you have, like because it's like a optimization problem. You don't know like how much the gamma affects to the final solution.
Yeah, so it's also, I guess, it's partially so sigma n, there's the variance of W, and so the variance of the noise depends on the loss function. And so if that's done exactly right, then that should line up with your core statistic that's used in the penalty. So of course, the variance of your noise will need to change in both problem. But then I think if that's exactly right, then gamma equals 1 will add equal amounts of noise to both problems.
Okay, thank you.
Thank you for the presentation. I'm also curious about the noise level. So in my understanding, it is like a hyperparameter for your model, right? So you need to tune it. So when you tune it, I think you need to be careful about introducing further bias. Like when you try many different levels of noise and select the best one, you are running the model over and over again, and you are like, how do you tune that noise value depending on the problem?
Yeah, so I actually, we haven't investigated too much about, typically we think of gamma being a constant that you would set beforehand. So with sample splitting, people often will just assume 1/2, or maybe you do like a 70-30 or 70-20-10 split. So people kind of have heuristics about how much information they put into their buckets. And at least I'm not super familiar with, in the sample splitting literature, people kind of, should I do half my samples for selection, for training a model, or should I don't know if people play around with that too much. But I think it's an interesting question for here and for there, but we haven't looked into it too much. It would definitely, as you change gamma, you're going to change what kind of model you select, and there's a trade-off. I think there's some papers that, it's something that we need to still sort of look into.
Okay, thank you very much.
So if any quick question? Okay, so it's time to close this presentation. Thank you.
So let me start my talk. I'm Masaaki Imaizumi, mainly from the University of Tokyo. First of all, so I have to say that I really glad to be here, and thank you for organizing this nice workshop. So then I have to say that I'm the only person who do not speak to talk about the selective image. Totally fine. And so I believe that I'm from the statistics field. So and I'm really interested in the statistical inference. And also, I'm also working on the learning theory or machine learning. So, and my another motivation, besides interest, is the kind of the theoretical understanding of the deep learning or AI architectures. Anyway, so and here I talk about the kind of how to combine the kind of the deep learning theory-based theory advance and the modern statistical inference, especially the high-dimensional statistical inference. Yeah, that's my today's talk. So anyway, so and then that's my interest. Anyway, that the high-level introduction is that all of you must know the recent success of a large-scale modern data science, including the deep neural networks, transformers, AIs, blah blah blah. So many large, huge, large-scale, nice architectures, algorithms, data, big data, blah blah. So and we know that the modern data science utilizes a very complicated large-scale models and algorithms and really successful and it's completely interesting research targets. Okay. So, and my personal motivation is that how to fully connect the kind of the large models and a more statistical rigorous inference. That's my high-level motivation. So of course, I mean the Takeuchi's team has had very actively working on the kind of the inference for the deep learning, so they're really nice results. And also additionally, so and I also interested in research topic. And so of course there are many nice results, but some aspects are not not so complete. So and my interest is how to implement, how to realize the rigorous, rigorous means that fully a descriptive statistical inference for the such modern data science large scale models. So as you know, I mean of course there are many uncertainty quantification method approach technologies for the deep learning, but they are still theoretical black boxes or unknown points, which prevents us to implement the complete version of statistical inference for the deep neural networks. Anyway, so I will explain what this complete means later. Anyway. So and basically to working on the more exact statistical inference, we need to know or specify or characterize the kind of the outputs of distributions under null hypothesis in basically. So in a sense, if you assume the kind of the null hypothesis and algorithm behave like this, and in this hypothesis, they put the distributions like this, and we can measure the p-values or statistical significance levels, and we can implement a rigorous statistical inference. So, but it's kind of almost impossible in this deep learning. And what is difficult is that there is a really complicated dynamics inside the deep learning. That's one of the, I believe that's one of the most difficult points. So, as you know, in the classical statistical models, linear regression or any other GLMs or any other supported vector machines. So, there are many of those functions are convex convex function. So then we can easily specify that what is the minimizer and what is the output of your algorithm, especially the risk minimizer. So and if you're a statistician, you may know that if our estimator is minimize those functions, so we can enjoy the nice expansion. Then we can enjoy the symptomatic normality, and then we can calculate a Gaussian limiting distribution. Then we can enjoy the really rigorous inference. That's the kind of what classical statistics did. However, in contrast, of course, in the deep learning, the neural networks, many of those functions are non-convex like this. So and it's many local minimas, many paradox, and it's not easy to achieve the global minima. And we cannot guarantee that your algorithm can reach the global minimizer. That's kind of the basic difficulty. So and so this figure is still non-convex, but it's one dimension, so it looks easier. But actually, the practical neural networks has very high dimensional dynamics on the very high dimensional functions. So this is kind of a very famous illustration visualization of the non-convex function in the high dimensional parameter space from the resonates. So and in practice, your nice training algorithm like HGD or ADAM search over the least complicated function in the high dimensional space. And so this is the two-dimensional by the dimension reduction, so we can visualize it. But actually, the original dimension is 300,000. So and we cannot visualize this in the real loss function, and we do not know what their goal, like where they achieve, where they reach. So in that sense, we cannot fully specify the kind of the description of the outputs of the algorithm for neural networks. And of course, more layers, loss function becomes more and more complex. So in that sense, it's like more deeper models, everything is much more difficult. So in that sense, like my understanding is that like high dimensional dynamics is obstacle for everything for the like theory and the mathematical statistics, I believe. So so this is the initial deep neural networks, and so we update the weights of the networks by nice, really highly efficient algorithms. But it's theoretically it's a totally black box in many cases in general. So in that sense, we cannot specify the distribution of the outputs. That's the kind of the, like a limitation. So so this like unknown distribution prevents us to working on the like a very like a precise statistical inference, I believe. So in that sense, my like our like a very basic and large question or like a challenge is that like we wanna describe the training dynamics for the deep neural networks in order to fully characterize the outputs of the deep learning. That's kind of the, like my large question. Okay. Then based on this introduction, so I talk about some challenges from my research group and also its potential future goal. So in that sense, the firstly, so I will talk about the like first research, which is kind of more it's not for the like a statistical inference, but it's try to describe the like for dynamics of the deep neural networks. And my second part is like mostly more for inference. It's not for neural networks, but we try to develop the statistical inference for the high dimensional nonlinear models, including the single index models. And so this is the like two like still already open the preprint paper, like a paper preprint paper open in the archive. So I briefly after that I briefly mentioned that by combining these techniques, we may be possible to develop the statistical inference for the like fully trained deep neural networks in future. But if we miss like in 2 or 3 years, I believe. So we are still working, already working on this like some projects in final goals, and we can open this result in not so far. But anyway, so today so I talk about this the research 1 and research 2. Okay. So I go to talk about the first one. So first one is it's more like comes from the deep learning theory. So of course close to the connected to the statistical inference, but it's not main inference is not the main interest. Anyway, so I write this paper. We write this paper and it's open this archive. And I titled it Precise Gradient Descent Training Dynamics for the Find with Much Layer Networks. And this is the collaboration with the great co-author with Jian Han from Rutgers. He's a faculty in this university and he's a very like a genius mathematician. And yeah, he had a very nice result. So outline is that we try to precisely understand or describe the dynamics of the deep neural networks asymptotically. So that's our topic, and there are many challenges, and there are many open questions. So especially our purpose is that we try to specify the output of the distribution of the training algorithm for the like deep neural networks. That's our purpose, and technically we applied some nice or more like a mathematical physics based theory GFOM. And which is an extension of the MP. I will describe that later. Anyway, so we apply this approach techniques and derive the result. Okay. So first, I describe the kind of mathematical setup, which is a really like a standard, I believe. So first, I focus on the neural networks with more layers, deep layers. Like L is depth, Q is width, and M is feature dimension, like dimension of each data point. So the W is a weight matrix for each layer, and bold W is like a tuple of all weight matrices. Sigma is activation, smooth one. So and FW is a kind of this is a very standard function by the like a deep neural network model without bias parameters. So I think a very standard definition. So, and we consider a really simple regression task. It's also very simple. So suppose that we observe the like n pairs of the inputs x and output y. So n is like a sample size. Then like x has m dimension and y is a scalar. So and we also like technically we assume that this data points comes from this like a single index model like this. and it's not very critical in this talk, but technically it's very critical. So, and with these data sets, we define the empirical squared loss function. It's very standard, I think. So, and also we define some additional notation, like a pre-activation value. So suppose that we have the we already have the models and the data. So we define the like a data matrix like this. Then we define the like some matrix which contains the pre-activation values, which is the set of the vectors which is the before the like activation function for each layer. So and this is like the pre-activation for the first layer. Then if you put this matrix to the activation function, we get the outputs of the first layer. So and for each layer we have the like a z, which is kind of the, like the pre-activation for the other layers. So that's the notation. Then okay, so we are back to the like standard setup, including the gradient descent. It's a really like a simple. It's extremely simple, I think. It's within the textbook. So and the bold W is a tuple of the weight matrices. Then for each time discrete time t, we have the running rate. Then update the weight matrix by the, like this. By it's kind of like a flow batch gradient descent. Okay. No SGD, but our result can be somewhat trivial extended to SGD. So in that sense, we focus on the GD case. So in this research, our interest is like a precise analysis of the dynamics of the like a true function, like a trained function. Okay. So in that sense, like our target is like this. We try to represent this output function by a tractable analytical mathematical formula for each t. T is finite, okay, not infinite. So T is finite. So and we try to theoretically derive the mathematical form which satisfies this equality, not inequality, it's equality. So and for theoretical requirement, we consider like a high dimensional and a large sample limit such that n and m diverge to infinity. Then the ratio at m over n converges to some finite constant. So and we try to specify the kind of the distribution of these outputs for each t. So note that so our goal is not an order. So but we try to specify the exact value asymptotically in this limit. So that's our interest in this paper. Okay, so and before going to our result, we briefly review the kind of the research background of this precise dynamic analysis for deep neural networks. So as you know, like deep learning has kind of has many theoretical puzzles, and it can, in that sense, like in these 10 years, like many nice researchers has joined this research fair and developed a deep learning theory with a new results specialized to the deep learning. So and precise analysis is kind of one of the active area research topic in the deep learning theory. So and because the precise analysis is very nice to cover the kind of like weak points of the classical learning theory. So and the very roughly speaking, the learning theory has some error. So error means that like that doesn't mean that like incorrect. That's the error means that the classical learning theory evaluate the like deep learning by using the inequality. Inequality means that our value the size of the error is like no more than some constant times some value. That's kind of what classical theory did have done. So in that sense, there are some like some errors. Errors means like there are some like the unknown constants. Like they can say that this error is smaller than this value up to some constant. That's kind of like very common in the learning theory, and we can describe kind of the convergence rate of these errors. And it's very useful and tractable and interpretable. And I also really like this kind of theory. But the weak point is that the description is not so rigorous. So and in that, of course, sometimes like non-rigorous is not so problematic. But in the deep learning dynamics, like this non-rigorousness is really like some of the limit have a large limitation. So in that sense, instead we are more focused on like precise analysis. It means that like we put more assumptions and more limited setups, but it can describe the real loss values in precisely like this. They can rigorously describe the kind of the actual value of the outputs or loss of the trained neural networks. That's our goal of the precise analysis. So yeah, in that sense, like training process for the deep networks is really very complicated. So in that sense, like classical theory does not help. It's useful but not very useful. So in that sense, precise analysis is really have attracted the attention in the research field. So anyway, and of course, and yeah, this kind of the other topics, but the dynamics of the neural networks is studied because of that. I believe that these dynamics are kind of the key to understand understand the actual deep learning or AI, I think. So and in course to the static analysis, like a dynamic analysis can precisely describe the outputs of the parameters. So in that sense, yeah, it can be a key factor to resolve the many statistical puzzles of the neural network theories. So anyway, that's kind of some motivations. So and also I try to describe some key notion. Toward the precise analysis, the key notion or technique is the distribution of the neurons or pre-activation values. It means that okay, so there are this is some the deep neural networks and some many layers and many neurons, and these are millions, billions neurons, and it's almost impossible to track their values one by one. Yeah, because it's too many. So in a sense, instead, we are considering studying the kind of the distribution of the values from the many neurons. So yeah, this images like this. Many neurons for each layer. Then we can consider kind of histograms, and we can study how the value of the activation distributed. So by using this notion, we cannot specify, we cannot study just the specified one neuron, but it's out of our interest. It's totally useless. But instead, what we want to know the kind of how they are distributed. So and the advantage is that if we put the width to infinite, so we can achieve some of the Gaussian-like limiting distribution to which this interpretation converge. So and Gaussian is a really nice distribution. Yeah, because only we have to know that mean and variance. So the only two parameters are sufficient to describe the kind of the distribution of the neurons, and this distribution is sufficient to describe the kind of the macroscopic property of the deep neural networks. So in that sense, yeah, this is really useful, and it can be like a strong target of interest of the recent some kind of the theoretician and the mathematician and the physicist. Yes, please.
So does that apply with respect, regardless of the choice of the W?
Yeah, of course, I mean, yeah, it's very critical point. And the firstly, of course, the choice of W strongly depends on connected to the description of the distribution. So, and then how the updated value of the specifying the distribution with the W after training is the key research topic in this research field.
So you assume that the W is already trained and fixed.
Yeah, it depends on the studies, and this simplest version is before training, just initialization. So, but in our research, we try to specify the distribution of the W after training. So,
Okay.
Yes.
Okay. Yeah. Sorry for interruption.
Thank you very much. Yeah, it's a very critical point. So, and this is a very rough overview. And maybe 10 years ago, we can enjoy this Gaussian distribution before the training. But of course, what we want to know is after training. So, and many studies to try to specify the distribution after training of the W. Then it's kind of like an ongoing just topic. Yeah, and then yeah, it's kind of a critical point. That's the next page. So and yeah, this is the many studies which try to specify the distribution of the Ws after training. So and one famous study is NTK theory. And before that, I have to say that this what axis means. Okay, and this horizontal axis is how your setup is simple and more actual real. Simple means like lazy regime or something. And this vertical axis shows that how your network, how deep your network is. And this bottom is a shallow network, like a 2-layer, and more up is a more deep network, some more layers. Okay. So and these four studies these four research achievement studies the distribution of the pre-activation after training. So and if we consider the lazy regime, the NTK theories are really useful, and it's utilize the linear approximation of the new network spaces, and it's linear. So and our updates are really easy to track. And another famous one is the mean field theory built by some nice researchers. So and it is a more complicated theory, but it can track the more actual non-lazy regime. But the limitation is that it is designed for the two-layer neural networks. So another more recent research is the dynamic mean field theory. It's kind of the dynamic version of this the second topic. And this is designed for the deepness after training. And it comes from the physics, theory from the physics, and it's a very general and a very active research topic. But the limitation is that they are not so mathematically very rigorous. So in that sense, we can guarantee that its validity only for two layers. That's the limitation. So and another really famous one is tensor programs that are kind of developed by the computer scientists, and this is designed for the deepness and after training. So many updates is okay, and many areas are also okay, but some critical limitation is that they achieve the kind of the mathematical formula to describe this limit, but it requires the exponential time to numerically calculate the mathematical formula. So that kind of limitation. Anyway, there are many nice studies, and but there are some obstacles or barriers to describe the actual real deep neural networks after training. And based on situation, so I try to describe our study. So first, so we should focus on the finite width case. This is kind of a small thing. So we focus on this setup like this neural networks. So input dimension is the m, and m divides to infinity. So but after first layer, the width is finite, so very narrow, deep, but narrow networks. And the design of this model is practically motivated by the actual architecture of the many deep nets, ResNet, transformers, GPTs. So of course the depths and widths are large, but the sample size and his dimension is much larger. So in that sense, we believe that finite width is a really kind of reasonable choice. Okay, and the more mathematical technique is so we utilize state evolution theory. So very roughly speaking, it's a really complicated theory, but very roughly speaking, so it kind of it's a mathematical way to generate the sequence of distribution of parameters or the pre-activations with reducing the time correlation comes from the iterative training algorithms. So it's really complicated, but very roughly speaking, okay, so if we consider the original gradient descents, we want to track the time transition of the distribution of the pre-activation. However, so there are some mathematical obstacle such that at initialization this distribution is like a Gaussian. Each initialization, so W is Gaussian initialization initializes as a Gaussian distribution. So and as the initialization is close to Gaussian. However, as time passes, so it's changes. The shape of distribution is getting far from it's getting far from Gaussian. It's more heavy-tailed cases. So this change of the shape comes from the correlation among time. It means that so because this is the batch gradient descent, so we reuse the data. So in that sense, there are many time correlation comes from the data reuse. So in that sense, after many updates, it is somewhat mathematically impossible to describe or track the shape of this distribution. It's kind of very critical here. However, we have there are many nice physicists and mathematicians developed the kind of correlation term named the Onsaga correction. So it means that if you put some correction term inside the algorithm, like a virtual algorithm, so we can guarantee that for every time point, for 10 times 1, 2, 3 to 100 to 1000, so every the distribution of the pre-activation is like a Gaussian. So that's kind of the nice mathematically nice point. So because they are Gaussian, so we can easily track how they change. So only we have to know is that a mean and variance of this distribution. So in that sense, we can fully track the transition of this distribution. So we can precisely describe the behavior of the like a neural net or like a dynamical algorithm. So in this sequence or wave sequence, during the sequence is known to be like a state evolution. So there are many technical interesting points, but yeah, but anyway, so only we have the very just very introduction. So this like state evolution is like utilized in the some more like a simple algorithm. This is not for neural networks. It's for linear regression. So that is a very most famous algorithm to which can describe the state evolution, I believe. So and okay, we first consider like a linear regression case, like yeah, square loss function plus penalty, like a L1 penalty or L2 penalty. So and to solve this point, this optimization, so we can define the AMP algorithm, then defined by like this. And eta comes from the kind of the like a penalty term. So this is the residual. So and the key point is that there's some strange term appears. So if we do not have this term, this update is a very simple proximal gradient descent. But this algorithm put this term here. And this term omit the time correlation comes from the data reuse. So and by using in that sense, after we can describe the output of the algorithm by the state evolution, which is fully Gaussian, so we can easily track the distribution of the elements of this output parameters by Gaussian, which easily mathematically track this distribution. It's very easy to describe the like full dynamics of the algorithm. Okay. Anyway, so and then we use and then this MP is kind of like a classical algorithm for the more simple models. And to apply this model to the more complicated models, so another researchers have developed a very nice more general algorithm like a GFOM, general first order method. And the definition is somewhat like a complicated. So I do not explain these details. But it's kind of like this is also like algorithm to reduce the time correlation. And the more they can calculate a more longer time correlation. So and as you know, if we update the parameter at time t, so they can reduce the correlation from the every past, like from time 0 to t minus 1. They can correct the correlation from the between these time points and time t. So and yeah, like it's more like a stronger way to reduce the time correlation, and which can be valid in the more complicated models, including the deep neural networks. So anyway, that's kind of like a rough overview. It's technically very complicated, but I believe it's very interesting techniques. Anyway, so and by utilizing this result, this is our theory. This is our result. So and we study the dynamics of the two many layer deep layer neural networks with finite width by this strategy. So this is our neural networks, and then yeah, only first layer, input layer, are going to the infinite dimension. So and we make the dimension diverge to infinity. So and we can describe the like a distribution of the pre-activation of the first layer by using the state evolution, which is like a Gaussian. It's very easy to track. Then from the second layer to last layer, so only we need like is like a finite width nonlinear transformation. It's in the sense it's more like it's not from the state evolution. It's more like easy to deterministic updates of the first evolution at the first layer. So that's the kind of state evolution at the first layer. So this is our strategy. So in the anyway, the proof is very complicated. So I try to briefly describe the outline of our proof of outline by this figure. Okay, so this is the time passes from the top to down. For each time, we have the pre-activation here, and without analysis, the standard gradient descent yields the like a pre-activation to the training loss function. Okay, so the first we put the correction, and we consider kind of the virtual algorithm with correction. Then we can define the corrected version of the pre-activation like this. Okay, this is like a m-dimensional random variable. Then so if we put the m to infinity, so then we can achieve some nice Gaussian, almost Gaussian. So and by central limit theorem. So this is a slight evolution. Then so we can fully describe the transition by using this Gaussian. However, this comes from the like a virtual algorithm, not the gradient descent. So we pull back this Gaussian distribution to the more original gradient descent version of the dynamics of the gradient descent. Okay. So this is the like just an image. So we have the gradient descent. The activation behaves like this. So then for the analysis, in the proof, we virtually consider the state evolution with correction. then put like a limit and achieve the Gaussian, then pull back this Gaussian to the original graded descent. That's kind of outline. Anyway, it's really complicated. Anyway, and and this is kind of like a part of the important mathematical formula to specify the output of the deep neural networks. Anyway, first we define like a matrix version of the Onsaga correction, which is a term to correct the time correlation. So between the for every time points, like the definitions are very complicated. So and I just put the outline. Then we have put the correction. This is the original activation, pre-activation. Then we put some the corrective term by using the Onsaga correction and some other pre-gradients. Then achieve this correct version of the pre-activation. Then by we consider the limit version of the pre-activation, activation like this. This is the Gaussian. This is the calculated for U is the Gaussian term. Then so we achieve this the Gaussian process by this covariance like this. Then using this calligraph U, then we define we pull back this calculated U to the some value which corresponding to the actual pre-activation from the gradient descent algorithms. So and then so this is our the part of the main theorem. So suppose that the data has a nice properties and activation function is somewhat smooth, then we can prove that the distribution of the value of the pre-activation by the gradient descent is asymptotically converge to the theoretical our derived theoretical value of the corrected corrected version, not corrected, corresponding state evolution. So this is the theoretical value, so we can calculate this value just from the mathematical formulation, no algorithm. Then in that sense, this is actual outputs of the algorithm, and this is a mathematical form. So in that sense, we can specify the distribution of the display gradient pre-activation by just the analytical mathematical formula. So this is kind of a consistency theorem for the first state evolution. But as a trivial corollary, we can derive the theoretical limit of distribution of the output of the deep neural networks after training, T times gradient updates. So anyway, so we check the agreement between our theoretical value and the practical outputs, and for many layers. So in a sense, this is the generational error, and this is the horizontal is update time, and we can see that the blue is the actual value, and green and red and the theoretical value with the different distribution of the data. Then we can achieve the agreement between the theory and experiments. Okay, so this is the first summary, and then we try to precisely describe the dynamics of the deep neural networks, and also we try to generalize the generational error, and we utilize the G form, and the results that we fully specify the precise description of the deep neural networks. Anyway, so the very roughly speaking, so what we achieve is so we open a kind of the black box of the training dynamics of the deep neural networks. So we can fully specify the distribution output. So it's really useful, we believe. So and also this is valid for the many layers and more easy to calculate numerically. So in a sense, I think with kind of general result. So we believe that this is kind of a study. Look at here, it can analyze the real and deep neural networks with many updates. Okay. So this is the first result, and also I have the second result, but we have no time, so I can skip here. Anyway, but somewhat related, but I think that this point is more close to the final goal. And okay, so I have 2 more slides. So yeah, and I briefly mentioned the kind of the future potential possibility to apply this our current result to the inference for the fully trained the deep neural networks. So and I believe that we may be ready. So now we have the full description of the training dynamics of the deep neural network. So in a sense, we can have an analytical form to specify the output distribution of the trained deep neural network. So and it's almost close to Gaussian or transformed Gaussian by non-linear transformation. So in a sense, we can specify this distribution. So and we can discuss the kind of the p-value like something or FTI control. So yeah, there are many others. So in that sense, so I believe that it can be useful. And actually, so our team are now working on the kind of statistical inference of the deep trained neural networks with incorporating the theoretical description of the training dynamics. And I hope that we can open the result in 1 or 2 years, I believe. Anyway, so that's all for my talk. Thank you for listening.
Okay, thank you. Is there any question or comments?
Yeah, thank you so much for a very fascinating talk. But in order to understand clearly, I would need to ask you many questions. But I just want to confirm first point is that so Onsaga collection seems to be very interesting. But so what you used? You used Onsaga collection in order to derive the. Could you go to the page 21 maybe? No, 31. Yeah, the consistency. Sorry, your consistency results. Sorry. Yeah, this one. Yeah. So in order to derive the theoretical value, you use just Onsaga collection.
Not only use the Onsaga collection, like I mean, yeah, it's very critical, technically critical point. So
yeah, this point is
yes,
very.
yes. So this is this term is the Onsaga collection is necessary to derive this Gaussian.
Yes.
So, but this Gaussian is comes this limit comes from the algorithm with correction with Onsaga correction.
Yeah.
But the actual gradient descent does not have a correction. So it's kind of like some gap between the gradient descent and some algorithm with Onsaga correction. So and we have to pull back. We have to we have to derive the distribution corresponding to the actual gradient descent. So in that sense, we have to one more step. First we derive this one Gaussian, then we derive another form from this series of Gaussian. That's another next. This is a more additional step to pull back this Gaussian to some distribution corresponding to the gradient descent.
Yeah. So that point is seems to be very mysterious for me. So yeah, by introducing Onsaga collection, the analysis becomes easy because everything gonna be Gaussian. But how can you say that? Did you think back from the Gaussian to the without the Onsaga collection can be done? Even when that way you cannot analyze. But
okay. Yeah. I think it's
some rough idea is
yes,
fine.
yeah. Thank you for a very important question. It's a very critical point. Yeah, I agree that your intuition in that sense. So I mean, we believe that the actual updates are really complicated, many higher order moments, very heavy tail. But this correction, only everything is from Gaussian. So it's kind of there seems to be an essential gap between the Gaussian sequence and the actual updates. I totally agree with this point. And this correction, of course, it's a very critical point. And this correction needs a more very sensitive control of the higher order moments of nonlinearity. So there are many complicated calculation which can control the higher moments. This is a more simplified case, but by utilizing simplifying randomness by using transform this simplified randomness to transform this distribution by using the more complicated nonlinear form. It's hard to say. It sounds difficult for me to say, describe in simply. But there are many complicated form which is highly nonlinear, which can transform this Gaussian to the more some distribution with potentially have a higher moment. So it's kind of a more a mathematically complicated equation is somewhat.
Yeah, but the more step you consider, the higher order term you have to consider basically, right? So you said that you somehow had to restrict the the higher order from some extent, or
yeah. Okay, I think you're right. So very intuitively, yeah, of course there are some limitation that there are some class of the limitations such there seems to be some limitation that this algorithm can be described by the kind of transformation of the Gaussian, but this algorithm cannot be described as the transform of the Gaussian. And in this case, so the key point is that we show that gradient descent is inside the class of the algorithm, which can be described by the transform of the Gaussian. So that's kind of a mathematically critical point.
Yeah, thank you. I need to understand them more, but thank you so much.
Thank you very much.
For now.
Any other comments?
Yeah, thanks for the talk. I have a question once again about this Onsager correction. So is it purely a theoretical tool, or does it have application? Like, I know here you're studying the regular gradient descent, but does the Onsager correction have application in terms of a modified version of gradient descent?
Yeah, so it's for both. So I'm not very expert about the history of the AMP. I mean, also correction. So, but only I know that the also correction is like appeared. It comes from the more physics, but I don't know the physics. So, and in this research field, like AMP is the most famous algorithm which have this also correction. Then, so and in practice, AMP is used for several machine learning algorithm in practice, like for practical use. It's known to be achieved like higher accuracy or very fast like calculation. So in the used the more beautiful propagation or some of the graphical models at the Boltzmann machine. So it's being used. And also mathematically, so some nice mathematician found that this correction has a nice property, also has a nice property in the mathematical sense. So this term is really useful to show the mathematical proof. So in that sense, some mathematicians use this as a correction as a proof device. In that sense, it's really useful in the both. Yeah, that's my answer.
Thank you.
Okay, thank you. So if you may have some questions, please discuss later. So now we want to finish this presentation discussion. Thank you.
Okay, good afternoon, everyone. So my name is Yui. So today I will discuss with you about post-transfer learning statistical inference. So in general, we will mainly focus on how can we assess the reliability of of machine learning results after the transfer learning process. Okay, so yeah, briefly about myself. So I'm currently a lecturer at the University of Information Technology, so Vietnam National University, and I'm also a visiting scientist at RIKEN AIP. Yeah, so I'm interested in like doing machine learning, data mining, and statistics. So recently, I'm also like interested in AI application in bioinformatics. So as we all know that nowadays, like usually traditional machine learning often require like large label data sets, but that is not always feasible in practice. Like, and in practice, in some domain like bioinformatics, we might have the data sets without any labels or very limited number of data in the data sets. And the key idea of transfer learning is that we're gonna reuse the knowledge learned in the source domain or the source task to improve the performance of the model in the target domain where we have the limited number of data. And because of that, like that's advantage. So transfer learning has become a standard in like many areas, and especially in the deep learning models. But like there is an important research gap. So after the transfer learning process, so how can we quantify the uncertainty of the result of the machine learning? So a traditional confidence interval or traditional p-value might break down, and this is because like if we just simply apply the traditional model, maybe we cannot like properly control the type 1 error or the false positive rate, because like in traditional machine learning, usually the observed discovery is assumed to be fixed before seeing the data. But here, like in machine learning, that assumption is violent. So in machine learning, so we observe the discovery based on the data. So in other words, we get the data first, and then we're gonna observe the hypothesis or the discovery by applying the AI or the machine learning on the data. So that's why when the observation is based on is observed from the data, then the traditional p-value is no longer valid, and we cannot control the false positive rate or the type 1 error rate. And one solution is selective inference. So Takeuchi or another speaker already talked about selective inference. So I just briefly summarize what is selective inference. So it's the very promising framework for assess the reliability of like data-driven discovery. So instead of using the traditional p-value, which ignore the selection process, so in selective p-value, we're gonna compute the probability of like seeing the observed discovery or more extreme discovery, conditioning on the process of how those observed discovery was made through the AI or machine learning process. So by considering this conditional property, we're gonna remove the selection event, or we're gonna remove the selection bias inherent in the AI or the machine learning process, and then the p-value becomes valid, and we can properly control the false positive rate or the Taiwan error rate. So this is the more detail. So first we observe the data, and then we're gonna apply the machine learning algorithm on the data to obtain the discovery. So here I call this is the discovery A. And then after having discovery, we're gonna do inference. And the main task is to identify some region. So of course, that region must include the original observed data, but this region also contain another data point, which whenever we apply the same algorithm on any data point in this region, we're gonna apply the same discovery as the observed data, these observed. And also, in general, these region can be characterized by a set of linear inequality. So in general, it's just a simple polytope or a polyhedra in the data space. And then we're gonna compute the probability of observing more extreme test statistics, conditioning on these on this polytope or on this conditional data space. So because of in selecting inference framework, we're gonna assume that the test statistics follow the Gaussian distribution, and these conditional data space can be characterized by a single polytope in the data space, and then this computation become just simply compute the tail probability of the truncated univariate Gaussian distribution. Then we have a straightforward computation for the selective p-value simply by using the software. And after having the p-value, we can conduct the valid statistical inference for the machine learning result for the machine learning result. And here is the example of lasso. Yeah, so Takeuchi sensei also discussed about this example. So I just briefly tell about this again. So we are looking for the association between the gene and the drug response. So here we have the data. So here our data is the random vector, which is defined as the sum of the true signal and the noise vector. So here the true signal is we unknown. So if we want to modelize the linear model, so this signal can be modelized as the inner product between the feature x and the coefficient beta. And the noise vector here, we assume it follows the Gaussian distribution with the no covariance matrix. And after having the data, we're gonna apply the lasso on this data to estimate the optimal coefficient beta hat. And then the set of the select feature was defined as consists of those whose optimal coefficient is non-zero. And then our question is that, so are these selective models truly significant? And we can use the hypothesis testing framework for address that question. So here we're gonna define the hypothesis. So the null hypothesis here is that we're gonna state the true coefficient of the feature beta j is equal 0. So which means that the feature j has no correlation with the response vector. And the alternative hypothesis H1 states that the feature beta has the truly correlation with the response. And then we're gonna define the test statistics. So we just simply use the original ordinary least square estimate to define the test statistic for the feature feature j. And after having the test statistic, we simply compute the p-value. So here is the difference between the traditional naive p-value and the selective p-value. So in this one, when we compute the traditional p-value, even though the test statistic here, so even though the the coefficient is defined based on the selected set of feature, but in the traditional p-value, we ignore the lasso selection event. So therefore, if we simply use the naive p-value, then we cannot control the Taiwan error rate or the false positive. But in contrast with the selective p-value, we're gonna compute the probability of seeing the random hypothesis, the random test statistic conditioning on the lasso selection event. And here, the lasso selection event can be characterized by the sets of linear inequality based on the KKT optimality condition of the lasso. And then we can compute the p-value straightforwardly, and we can conduct the test, the statistical inference for the feature selected by lasso. Yeah, so that is some example and briefly introduction about the selective inference and its application to lasso. And over the past 8 years, so I have doing research on selective inference in several directions. So the first one is supervised learning. So I do it for the generalized lasso and sequential feature selection. And for supervised learning, we do it for selective inference for dynamic time wrapping and optimal transport or change spot detection. And for rapid learning, so we do like for segmentation problem or attention problem. So all these like 3 dimensions, so they were primarily conducted when I was the master and PhD under the supervision of Takeuchi Sensei. And after returning to Vietnam, so I started mainly focus on like selective inference for machine learning result after transfer learning. So in this talk, so I will cover 3 main direction I have been recently focused on. So the first one is about like domain adaptation. So the second one is transfer learning in high-dimensional regression. And the third one is like I extend to very complicated setting where deep learning model after the deep learning-based domain adaptation. Yeah, so let's start to the first one. So selective inference from machine learning after the domain adaptation. So here I will mainly focus on the anomaly detection task and the feature selection task. Yeah, so let's move to the first one of like anomaly detection after the domain adaptation. So in this setting, we would like to like detect the anomaly in the target domain. So here the target domain is the patient in the hospital T. T here represents the target. So we would like to detect the patient with disease, and the patient with disease here can be treated as the anomaly. But in this setting, in the target domain, we only have the limited number of data. So if we just simply apply in the anomaly detection algorithm on this data, maybe the performance might not good. And this is the reason why we have to transfer. So we utilize the power of the source domain. And in this source domain, we have a lot of data, and we're gonna use some domain adaptation technique to transfer this data point in the source domain to the target domain to bolster the to improve the sample size, as well as the purpose is to improve the performance when applying the anomaly detection algorithm on the target domain. And then after transform all these data points to the target domain, then we're gonna apply the anomaly detection algorithm, and we obtain this result. And you can see that with this result, so I just here is the A, B, C, D, and you can see that without any inference, so the algorithm can select these 4 anomaly data points. But actually, if the data point A and B, the true label is no disease. So which means that the algorithm mistakenly detects some healthy individual as anomaly. So which means it's the wrong result, and it's might harmful for the patient if the doctor injects some like drug to their body, like for example. And if we see in the naive p-value, the naive p will always come out very small, even for those wrong detection. So this also indicates that the naive p-value or the traditional p-value is still unreliable. And with the proposed p-value, so in this one I call the proposed method is CADDA. So it's kind of controllable anomaly detection after the domain adaptation. So with the proposed p-value, so for those wrong detection, the p-value is large. So here like 0.42 or 0.63 for those wrongly detection, and the p-value is going to be very small for those like truly detection. So in this example showing that with the proposed method, we can tell apart from the foreign positivity, from the true positivity detection. So let's go to the more technical details. So in general, we have 2 stages, domain adaptation stage and the anomaly detection stage. So in the step of domain adaptation, so we starting this research with very simple method like optimal transport based domain adaptation. So the main reason is that first, because in the optimal transport community, this method become very popular and many people use this method. And the second reason is that this method is very fit to the selective inference framework. Yeah, and after the reason I was gonna tell later. And in the second stage, we consider a very simple anomaly detection algorithm. Although it's simple, but it's still very effective in the industrial. Yeah, so it's called like median absolute deviation. So like we compute the median and we just identify the anomaly based on the median absolute deviation. So the algorithm is very simple. And after that, we're gonna compute the p-value conditioning on both stages. So first we conditioning on the optimal transport based domain event, and then we also conditioning on the MAD events after the domain adaptation. So here the point is that how can we characterize this conditioning? So first, let's talk about the domain adaptation stage. So because like we use the optimal transport model, then the concept is just finding the optimal matching between the, so here blue is the source domain, and for example here maybe this is the source domain and this is the target domain. And the main concept is just want to find the optimal matching between the source domain and the target domain. And then based on that matching, we're gonna have the formula for transporting from the source data point to the target domain. And this is, for example, here in this case, this is the optimal matching, and therefore the characterization of this event corresponding to the characterization of this optimal matching. And here in more detail in the optimal transport, we use the linear program to find the optimal matching. And in linear program, there are some variable called basic variable. So the purpose in the linear program is first we're gonna identify these basic variable, and after having this basic variable, we can identify the matching. And after we have the matching, we can perform the domain adaptation. And therefore, the root is to how can we identify the basic variable in the optimal transport problem. And therefore, in final, so our goal is to, if we want to characterize the events of this domain adaptation step, we just simply consider how can we characterize of the event of selecting this basic variable. And we can simply characterize, and in the literature we can characterize this selection of this basic variable by the set of linear inequality. So first step, we have the linear inequality, the set of linear inequality. And in the second step, so to characterize the event of this MAD algorithm, we just consider every step of this algorithm. And in every step, we can also characterize it as the set of linear inequality, because in this median absolute deviation, we just simply use the absolute distance. So the absolute distance can be considered as can be characterized by the set of linear inequality. And in general, we have the first stage, one set of linear inequality. The second stage, another set of linear inequality. And in general, we have the entire process can be characterized by the set of linear inequality. And if we have the set of linear inequality, our selection event can be represented as a polytope in the data space, and we can compute the selective p-value similar to the case of lasso. Yeah, and then after that, we're gonna extend to the case of feature selection after the domain adaptation. So in this setting, we also use the same optimal transport-based domain adaptation, but the setting is different. So in the previous setting, so we're gonna focus on the anomaly detection, which is the unsupervised setting. But here we have the feature selection. So we focus on supervised learning setting when we have the feature matrix and we also have the response vector. And because we have the supervised learning setting, so that's why we're gonna stack the X and Y in one single matrix before performing the domain adaptation. Yeah, and after the domain adaptation, we also apply in the lasso to select the feature. And the goal is also want to introduce some selective p-value for the selected for the feature selected by lasso after the optimal transport domain adaptation. Yeah, so the process is very similar to the case of anomaly detection. So we also have the first space of transport domain adaptation, and they can be characterized by the selection of the basic variable. And the second stage is the lasso. Saying we can, for characterizing the event of the lasso, we also rely on the KKT optimality of the lasso. And then in general, in the whole process can be also characterized by a set of linear inequality. And then we can compute the p-value. And we can also extending this p-value computation for the elastic net selection and also for the cross-validation. So because here in the lasso, we have the lambda here. So we need some cross-validation to selecting the lambda, to hyperparameter tuning the lambda. And if we consider the case of cross-validation, we might need to add some additional event of the cross-validation in this conditioning. And that event of the cross-validation can be characterized by the set of quadratic, not linear, but quadratic inequality. So in general, we have the system of linear inequality, intersection with the system of quadratic inequality. And finally, we have some region or some conditional data space for computing the selective p-value. Yeah, and then we also extending the setup to the sequential feature selection. Yeah, so in sequential feature selection, we're gonna sequentially, step by step, adding the feature, selecting the feature so that the residual sum of square is minimized. And computing the selectivity also very similar. But here, so in the lasso, we're gonna rely on the KKT optimality condition. But here, because we use some procedure, some algorithm to selecting the feature, then therefore we need to, the characterization of this event also relying on the algorithm itself. So because so for each step, we're selecting the feature based on the residual sum of square, so which is the square function. So that's why the selection event of these procedure can be characterized as the set of quadratic inequality. And this setup can be also extended to the backward sequential feature selection or the hybrid method between forward selection, backward selection, plus some model selection. Like in this sequential feature selection, we need to specify so how many features we're gonna select, and we must fix those feature value in advance, or we're gonna use some feature selection criteria like AIC or BIC or adjusted square. And when using these criteria for selecting the number of features to be identified, so it also can be characterized by the set of quadratic inequality. So in general, the whole system one system of linear inequality by the optimal transport domain option, and another system of quadratic inequality by sequential feature selection or the combination of sequential feature selection and the AIC or BIC model. Yeah. And the computational of the p-value is also similar to the previous setting. Yeah, so until now we have learned about I have shared about the selective inference for traditional machine linear model for the optimal transport-based domain adaptation. But in the setting of high-dimensional regression, maybe applying the optimal transport-based domain adaptation might not working well. Because in those optimal transport problem, they may be good for the low dimensional setting, but for high dimensional setting, maybe it's difficult to find the matching. So that's why the optimal transport based method might not work well in the case of high dimensional regression. So that's why I want to extend this to some other transfer learning setting in the high dimensional regression problem. Yeah, and actually there are several work on the transfer learning in high-dimensional regression. So the first one is the transfer. So maybe this is the seminal work in the field of transfer learning in high-dimensional regression. So it was originally published on arXiv on 2016, if I remember correctly, but it's recently accepted in 2022. But in this paper of translasso, they require a lot of assumption. It's very mathematical problem, and they introduce a lot of some assumption. And recently, there are some development on this direction. And one of the latest method is called the transfusion, which were published in AI Stat last year in 2024. And this is the briefly of the procedure of transfusion. So in general, they have two steps. So the first step called code training. So in this step, so here, let's see, we have the in total 0. 0 here means the target task, and K from K equal 1 to equal capital K is the source task. So the goal is to like combining both the data in the source task and the target task to to estimate the coefficient. Like for the first one, they just want to utilize all the sample that they have from both source domain and target domain. And then after computing the estimate, they're gonna refining the estimator to simply using the data point in the target domain. So they call this step a locally biased. So in general, they only have the two steps. So the first step may be referred to the transfer learning step, and the second step is they just want to refine their parameter so that it's fit to the target domain. So that's the main concept of this transfusion method. And we're gonna focus on the provide selective inference for this transfusion method. But later on, we can also extend our method to translational or another transfer learning setting in the high-dimensional regression. Yeah, so it's also similar because we have two steps here. We're gonna compute the p-value conditioning on these two steps. And in this setting, we focus on feature selection. Then we're gonna provide the statistical inference for the selected feature after the transfer learning high-dimensional regression process. Yeah, so we also conditioning on the code training step and the local debiasing step. And here we can see that the first step also rely on the convex optimization problem. And the second one also rely in the convex optimization problem. And in general, this process can be, the first one can, the selection event of the first step can also be characterized based on the KKT optimality condition. And the second one is also can be characterized by the KKT optimality condition. Then we can also, directly apply the selecting framework in this setting. And we can also extend it to the translational. But in translational, they have two settings. The first setting, we need to specify. So the set of like the source domain, or another setting, if we don't know which source domain is informative, then there are some selection procedure to selecting the informative source domain. But those selection is very complicated, and it's not it cannot be characterized by the set of linear or quadratic inequality. So extending the selective inference framework for those settings is not currently not possible in my research. But for this kind of transfusion method, they don't require to specify the which data set is informative. So that's quite general. So that's the reason why I provide the selective inference for this transfusion method. And in this transfusion paper, they also introduce another extension. It's called detransfusion. So like in this setting, we're gonna utilize all the data set from the source domain. But maybe in some setting, they wanna prefer prefer the privacy. So they don't want to transfer the data, but they only want to transfer the parameter also. So this setting is detransfusion is for transferring the parameter only, not the entire data set. Yeah, but in general, our the selective framework can be also extended to that kind of setting. Yeah, there are also another setting called like federated transfer learning. So we can also apply extended this method to that kind of setting. Yeah. And this is the experimental result. So on the synthetic data and the real data set data. So here, no inference means that we don't conduct any statistical inference. And the false positivity rate is very high. So it's like we always identify the false positive in every iteration. And the blue one is the naive p-value. Yeah, so here, even the traditional p-value cannot control the false positive rate less than the level of 0.05. The red one is the Bonferroni. Yes, the Bonferroni is very traditional multiple hypothesis testing framework. But if we just simply use the Bonferroni, our method is very conservative. So the false positive always 0. And the data splitting also, in this case of data splitting, the false positive rate can be controlled at can be properly controlled at 0.05. But I will show that the TPR of the data splitting is lower compared to our method. And PTLSI, this is our proposed method, and the OCE another variance of our method. And in this case, with the proposed method, we can successfully controlling the false positive rate. And considering the true positive rate, so our method in the red have the highest power in the so which means we why we can properly control the false positive, we achieve the highest power in the kind of in true positive rate. And this is the experimental result on the real data set. So this setting is simply show that the p-value of the proposed method tend to be smaller than those compared to the another competitor. So this indicates that our method tend to have the more higher statistical power compared to the another competitor. So far I have been shared with you about the machine learning after domain adaptation and the transfer learning in high-dimensional regression. So our latest method research related to like deep learning models. So after deep learning based domain adaptation. So the story is that first I started this direction in 2024. So we just start with a very simple model, like simple domain adaptation and very simple machine learning model. But after that, we try to gradually investigate or extend our method, extended our method in more several setting and more very complicated model. So this is the example. So here we also have the source domain and also have the target domain. But then for the deep learning based domain adaptation, we're gonna learn the domain invariant representation. So we don't transfer anything, but we want to learn the domain invariant space. So it's kind of we use some like deep neural network for feature extraction, and we extracting the like invariant feature between these, the feature that share the common characteristic between these domain. And then we're gonna input the source domain to the feature extractor, and we have the output, and we also input the target data to this feature extractor, and we have the output, and they are on the same on the invariance latent invariant space. And then after having the data point in this latent space, we're gonna input to the autoencoder to find the anomaly detection. So the procedure of detecting the anomaly detection is that we maybe you already know that the autoencoder tries to reconstruct the original data point. So if so we train the autoencoder on the normal instant, but like so therefore the autoencoder have the ability to reconstruct the normal data point very well. But if we input the anomal data point to the autoencoder, then the reconstruct error is very bad. So that's why our goal is to define the top K data point that have the highest reconstruction error. So highest reconstruction error corresponding to those data point is the anomaly data point. And after detecting the anomalies based on these autoencoder model, so we also want to test whether the detected anomaly is truly anomaly or not by providing the p-value based on the selective inference framework. So in general, we also have two stages. So the first stage is the deep learning based model for the domain adaptation, and the second phase is the autoencoder based domain adaptation. And because like you can see that the whole step, the whole procedure simply just using the feed forward of the neural network. And these are the characterization of the selection event of the deep neural network. So we just rely on each operation in the traditional in the neural network procedure, like for example the ReLU or the convolution or the mask pooling or the thresholding, and all these operations can be characterized by the set of inequality. So in general, the entire process is just simply the feed-forward process of a neural network. Then we can characterize the conditioning event at the single polytope in the data space, and then we can provide the the selective p-value for the detected anomalies in this setting. Yeah, so know that the deep learning model will train in advance, so we don't consider the selection event of the training process here. And one of my students also try to, another bottleneck of this deep learning model is that the computational time. So the feed-forwards require us a lot of effort and a lot of time to proceed the feed-forward from the input to the output. And recently, we also try to leverage this computation to GPU server. I didn't show the figure here, but yeah, we also try to recoding. So use recoding and try to optimize the code on the GPU device. So by running this method on the GPU device, the time is it's very fast, and we try to bring this model to more practical usage of more practical usage and easy for the analyst for the analyst to easy to use. Yeah, and we also try to provide a package that people can just simply install and run this method on the GPU device. Yeah, but here we mainly provide implement on the NVIDIA structure. So if you want to extend to another GPU device not provided by NVIDIA, so we need to recoding again. Yeah, like we provide the specific implementation for the specific type of GPU device like that. Yeah, so in general, so I have showed that the selective inference is very promising for evaluating the machine learning or deep learning result in the post-transfer learning setting. And I have to introduce to you like how we apply selective inference for testing the result of anomaly detection or feature selection after the traditional optimal transport-based domain application and also deep learning-based domain application. And in the future, I think we can. So we currently also try to extend it to, for example, clustering setting after the domain application, or we try to extend it to very more difficult model. Like currently for the deep learning, we can also provide it to autoencoder, but we can also provide for more complicated or more recent deep learning anomaly detection model, not simply for autoencoder. Yeah. And actually, I see that in industrial, there are three models that they very use frequently for the anomaly detection. The first one is the XGBoost, the second one is autoencoder, and the third one is GANs. So I think there are those three models people use a lot in industry. So I think providing the very good implementation for those models maybe bring selective inference for more practical uses. Yeah. And we also try to develop some toolkit that people can contribute to to improve the selective inference software. Yeah. So that's all for my presentation. So thank you so much for listening. Yeah.
Okay, thank you for presentation. So is there any question or comment?
Thank you for your talk. Can I ask about your future plan? So you just mentioned about XGBoost, applying to XGBoost and other things setting. So is it obvious for you to how to implement this, or do you need some further research to understand?
Yeah, I need some further research to understand. Yeah,
but you anticipate that it is completely applicable.
Yeah.
Okay.
But it's more complicated. It's very complicated. The process of like XGBoost, because they have some in XGBoost they have some randomness process in the XGBoost. So yeah, it's not that kind of like straightly applicable.
Complicated but not impossible.
Yeah.
Okay.
Exactly.
Okay. Thank you.
Any other questions?
Yeah, thanks for the talk. Can you just, on the XGBoost comment, can you just, what is it exactly like the problem formulation that you're trying to solve with XGBoost?
So the XGBoost is also the classification problem. So XGBoost is just simply the decision tree model, and it can be applicable for the classification problem. So the anomaly detection can be considered as the classification problem, right? And abnormal and non-abnormal. So in this setting, the setting is that based on the classification output, we detect the anomaly. and then we're gonna testing those anomaly, whether it's truly significant or not. And the conditioning is that we need to conditioning on the attributes procedure. Yeah.
And then related to that, you had the like top K was used as an anomaly. Was that top K, like it's not in the sample itself, right? The test sample? What is it, the top K percent?
And the top K in the reconstruction space, not the original space. So from the original space, we're gonna identify the reconstructed data point, and then we're gonna compute the reconstruction error. So high reconstruction error indicate that that data point tend to be anomaly.
And it's the top K percent out of all the test points?
Entire data set.
Including the train ones, or?
In this one, it's not include the train one. It's, no, in this one, it's include the train one. Yeah, entire reconstruction of that. Yeah.
Okay, thanks.
Yeah.
In this, like some difference of the setting about anomaly detection, there are like completely unsupervised anomaly detection, or people sometimes say semi-supervised anomaly detection and supervised anomaly detection.
Yeah, exactly.
So maybe this is completely unsupervised, right?
Exactly.
And the one with the XGBoost is supervised.
Yeah. So there are two different settings. Yeah.
So like anyway, so now transfer learning is everywhere.
Yeah.
Like people have the foundation model.
Yes.
And they have their own data and update the model.
Yes.
So in that kind of general transfer learning setting, people usually use.
Yes.
Do you think this framework can be used? And what is the perspective and what is the task you need to resolve?
Yeah. So Sensei, so I'm gonna about the perspective of computation first. Yeah. Regarding the computation, so the deep neural network is very big. Yeah. But in this sense, so like one of my students tried to like very like 100 layer, and also like the width is 100 neuron. So we try to see like how much time we need to compute the p-value for very huge network, and then it's computable, Sensei. So it's maybe few minutes. So yeah, regarding the purpose of like computation, then I think it's not challenging for if we use the pre-trained model. Pre-trained model maybe 100 layer is quite big enough. Yeah. And for the setting, for the setting, so maybe people use pre-trained model for language model or something like that. And I think we cannot apply for the language model at the moment. But for the transfer learning setting in the computer vision, yes, I think it might be applicable. Yeah, for the tabular data or the unstructured data like image, then it's fine. But for the like embedding model in language model, then I think currently need to investigate more. Yeah.
So any other question? If not, so let's thank the speaker again.
Okay, thank you very much.
Thank you very much. First of all, I'd like to apologize that my research about selective inference does not proceed well. So this is a little bit old topics. And this is the flow of this presentation. After introducing causal inference, specifically propensity score analysis, I will give our contribution about a model selection method, non-asymptotic and asymptotic polyhedral lemma, and asymptotic control of false coverage rate with some recent developments. This is partly a joint work with Umezu-san, Takeuchi-san, and KU Ruben's group. The model treated here is this fundamental causal inference model, like this one. this large H, there are large H kinds of treatments, and this TH is assignment variable that is 1 if H's treatment is assigned and 0 otherwise. And this YH is a potential outcome which is observed if H treatment is assigned. And for this, so YH with TH equal to 0 are regarded as missing values, and actually just Y, this Y is observed value, observed outcome. And for this YH, we suppose this model, this model, and this X is confounders, and this mu H is regression function for H treatment. And later we assume this is linear function of X. And this F is a nonlinear function of X, which is common in all treatments. And actually F plus epsilon is regarded as noise, and we divide it into two terms. First one is X-related term, and this is a X-independent term. And for this epsilon, we assume Gaussian distribution with mean 0. Okay, and letting this C1 CH is a contrast with its sum equals to 0, and our estimate is Kato, conditional average treatment effect. This one, weighted sum of mu H with contrast CH. And please note that naively estimating by, for example, least squares method will lead to bias because TH and YH are correlated through confounders X. So the propensity score method is a standard method that does not yield such a bias by not estimating F, which is usually difficult to model. Selective inference in this setting is also treated by this paper, but it is eventually based on non-parametric estimation of F. This slide shows just notations and assumptions. We put subscript I on variables of I sample, and we put tilde for the correction of variables of all samples. So for example, Y tilde is Y1, Yn, and T tilde is diagonal matrix of T1, Tn, and so on. Then our model is expressed as this one by just putting tilde. And these assumptions, which is usual in causal inference. The first one is weak ignorability, that is Y, H, and TH independent given confounder Xi. And the probability of Ti equal to 1 given X, which is so-called propensity score, is not 0, actually positive. And all samples are independent. Okay, so in causal inference, inverse probability weighted IPW estimation is a standard approach which uses propensity score denoted by EH. This is the probability explained in the previous page. And in this estimation, missing values should be recovered by multiplying observed values by the inverse of the propensity score as weights. Then usual estimation is conducted. Specifically, letting WH is this weighted matrix by multiplying the inverse of propensity score, and define W is the weighted sum of WH using this contrast CH. Then IPW estimator is given by minimizing this weighted squares loss. Because the expectation of WY is actually this our target. And actually this estimator has consistency under assumptions explained before. Our purpose is selective inference in causal inference, in causal inference. And as a model for mu h, we consider a linear function of xm. This is confounding variables belonging to m, which is a subset of 1 p. And because the causal effect is this one, we define an estimand as this beta m, which is arg minimum of this mean squared error with respect to this bm. So this beta m can be written like this one. So our target can be written as x transpose beta true. Then this estimand becomes the true value. This is this is completely following the basic selective inference. And denoting the selected model as m hat, we try to find this confidence interval such that this probability of beta being included by this interval given m hat equal to m is larger than 1 minus alpha. Using unit vector ej, of course, beta j can be written like this one. This is beta m. So defining eta j like this one, this is this part. Then later we consider the conditional distribution of eta transpose wy, because wy is an unbiased estimator of this our target. Okay, so as our model selection method, we use lasso for causal inference. Specifically, considering that mu h linear function of x in our model, we propose this estimator using this L1 penalty term. And actually, this is a least squares used for basic IPW estimation. And let us denote m hat is an active set, and beta hat m hat is an estimate of beta for active set, and s hat is its sign. Then for any model m and any sign s, we can write this event of m hat equal to m and s hat equal s can be written like this way. This one, using where this A is and this B is matrix and vector independent of Y. So this is, of course, a polyhedral region in the space of Y. This is obtained by KKT conditions. Okay, so I'd like to point out a problem unique to selective inference for causal inference. And actually, unlike basic selective inference, y is not Gaussian, and fx exists. So, but this is just a conditional inference. So we can further condition large t equals small t and large x equals small x to obtain polyhedral lemma. By conditioning these, the problem becomes just a basic selective inference. This should be a key point. Actually, it is unusual to initially condition large T in propensity score analysis. So I want to say the proof is very easy, but it is a little bit difficult to hit on this idea, at least for me. Anyway, we can get this causal inference version of polyhedral lemma like this one. Under notation on the next page, the conditional distribution of this pivot statistic is a uniform distribution. Yes. The notation is, of course, too complex to explain, so I will skip. But I'd like to just say that this f is a cumulative distribution function of truncated normal with mean kappa j and variance theta j into the truncated region from v minor to v plus. And this eta transpose wy is a statistic explained before. And I want to say I conditioned t and x, but after conditioning, the pivot statistic has just a uniform distribution independent of t and x. So we can marginalize t and x, and we can get this theorem. But we still have a problem of the previous polyhedral lemma. Actually, it cannot be used for the inference about beta j because beta j does not appear explicitly in the pivot statistic. Actually, there is no beta j here. In basic selective inference, this kappa j is beta j. So no problem. But actually, kappa j is asymptotically equivalent to beta j. But in selective inference, it's not inappropriate. It's inappropriate to replace kappa j with beta j. So we consider higher order asymptotics and extract beta j from kappa j. And from calculations frequently used under ignorability condition, then we can get this asymptotic polyhedral lemma. If y dagger is asymptotically equivalent to mu h plus f, then the conditional distribution of this pivot statistic is asymptotically this uniform distribution. Here, then we can get beta j here. And please note that this higher order correction term, tau j, converge to 0, but this higher order correction is necessary. Okay. Okay. And similarly to basic selective inference, we can increase power using a union of intervals. Specifically, if we want to condition just m hat equal to m, we have only to use truncate the union of intervals as truncated region. So we have only to just put union here. Then the polyhedral region becomes just this one, and we can get this theorem. And since pivot statistic is monotonically decreasing with respect to beta, so if we set L and U to satisfy this one, actually L and U here, and this is 1 minus alpha over 2 or alpha over 2, then we get asymptotically guaranteed conditional coverage like this one. The probability of beta j being included in this interval given m hat equal to m converges to 1 minus alpha. Okay, and I'm sorry not to explain about how to define y dagger because of needless tedium, but we can define it appropriately, and actually we obtain, for example, this equality from ignorability conditions. It means that this higher order correction provides asymptotics a little bit faster than usual because this order is n minus 5 over 6. Anyway, if we set L and U to satisfy these explained before, then we can control asymptotically the false coverage rate like this one. The limit of the expectation of the rate of beta j being not being included in this interval is less than alpha. Okay, so this is a simulation studies about evaluations of coverages. Here we compare selective inference SI and naive inference NA. And f is 0 or linear or nonlinear. And x is discrete or x is continuous. And please focus on these values of false coverage rates. And these values are for selective inference here and here are almost 0.05, but these values for naive inference are much larger than 0.05, like this one. So naive inference cannot control the false coverage rate at all. Okay, so this is a typical example of confidence intervals. Yes, actually, these values are indices of selected variables, and the true values of their coefficients are 3, 1, 1, 1, 1, 0, 0, 0. So even if these three values are selected, post-selection confidence intervals is expected to include 0. contains 0. So, and actually selective inference contains 0 like this way, but naive inference does not include 0 at all. And this is a real data analysis using benchmark Lalonde data set. Yes, and yes, in this analysis, causal effect is set as a difference in annual income in 1978 between the group taking the US job training program and the group not taking it. And by Lasso, 5 variables, these ones, were selected among 10 variables. And this is a confidence interval. And please focus on this income 74. Selective inference, confidence interval for selective inference contains 0, but naive inference does not contain 0. So we don't know, of course, which is true, but anyway, their results are different. In Pirene et al., we have mainly 2 developments in methodology. The first one is explicit calculation of this truncated region, which is a boundary of polyhedral region. Referencing the result called parametric programming by Nguyen Takeuchi, we provide an expression that is the same as this result if it is not causal inference. So this is just a generalization of this result. On the other hand, we couldn't understand how this paper demonstrated that the calculation allows no omissions of the candidates of these boundaries, and this calculation is a finite operation. So we provided a slightly different demonstration using the continuity of the estimator. Additionally, we gave a calculation method for using adaptive lasso when covariates orthogonal, although it may not be very practical. The second one is selective inference for database determination of regularization parameter. Using Stein's unbiased risk estimation theory, we can derive a CP-type information criterion, which is an unbiased estimator of the mean squared error, in order to determine the regularization parameter. And the selective inference conditioned on which regularization parameter was selected is also proposed by this paper in the framework of cross-validation. Yes, actually, in the previous presentation. So our contribution is to construct a selective inference in the framework of information criterion, where the selection of the regularization parameter is marginalized and only the model section is conditioned on. On the other hand, this idea of marginalization is already existing. For example, Shirai-san's paper. Yeah, I'm sorry. I heard from him that this is published in ICML this year. Sorry. So we have merely confirmed its feasibility in the framework of information criterion and causal inference. Okay, so let's conclude. Conditioning on the assignment variables first. This is unusual in propensity analysis. And using higher order asymptotics, which is also unusual in selective inference, we have developed asymptotically guaranteed post-selection inference. And the numerical experiment showed that method that ignores the quiet scandal of statistics. So naive method results in significant deviations from the preset coverage of the confidence intervals, but our method maintains the coverage. And since these results cannot handle even generalized linear model-based causal inference, we'd like to develop the result of this paper into a causal inference version. And as I show in this numerical experiment, selective inference or post-selection inference is definitely indispensable. But I think the formula seems complicated and it hinders the widespread use among users, I think. So, of course, the development of package and manual is an urgent issue. Okay, that's all. Thank you.
So, is there any question or comments?
Yeah, thank you so much for a great talk. So I would like to ask about your experimental result about the confidence interval showing the black. Yeah, this one. So even in the numerical table, I am wondering that usually the naive inference confidence interval tend to be smaller than the selective one. So, but I don't see this in your case. So, for example, maybe you can go back to the table, true positive and false positive. Yeah, here, compared with between the selective inference and naive inference. So, of course, the false coverage control is fine in selective inference. So, but the true positive rate are almost same between selective inference and naive inference. So it's a kind of like true positive and true negative is a kind of trade-off thing. So
yeah,
it seems a bit strange to me about the closeness of the true positive rates in this experiment. So if there are something hidden here, so yeah. So I'm just wondering.
Yeah. As you say, our setting is a little bit inappropriate. So yeah, so maybe the true value of coefficient is too large in this setting. So true positive becomes almost the same value.
I see. So like if there are very like sensitive setting, like whether the true coefficient is not very huge and okay.
Yes, right. we must do such a simulation study. I didn't find it. Yeah.
Okay. Thank you so much. It's now cleared. And my next question is about, you talked about union of intervals.
Yeah.
So in theory, of course, I can understand that it suffices like this. But in terms of the computation, do you actually consider the union? Have you considered the union?
Yes.
Case? So how do you compute then? So
yes, yeah, I just use parametric programming.
Okay, you use parametric programming.
Yes, but before I didn't use such a programming method. For example, to make this simulation study. But after that, in Pirene et al. Sarah made parametric programming.
Okay, so this means that even in your problem, in order to avoid a kind of over conditioning, the parametric programming or line search type of approach can be useful.
Yes, yes.
Okay, thank you
very
so much.
useful.
Nice to hear that. Thank you so much.
Thank you very much for the talk. So I just have one question about the overconditioning. So in this kind of like causal inference, so could you clarify what is the overconditioning in this kind of causal inference task? Like we have like overconditioning, we're conditioning a lot of things, and we use parametric programming to remove the overconditioning. So in this setting of like causal inference, so I'm wondering, so what is the overconditioning in this causal inference setting?
Yes. Yes, we have, first of all, we have same type of over conditioning in basic selective inference. And in addition to such over conditioning, we have more over conditioning because we condition large T. Large T is an assignment variable.
Okay. So assignment variable in causal inference.
Yes. So it's too over conditioning, but even so, it's very useful comparing to naive method.
Okay. But I wondering, so so the conditioning on that T is redundant or is like compulsory? It is compulsory or is it redundant?
Redundant. Yes.
Redundant.
Redundant.
Yeah.
Yes.
Okay,
Redundant.
okay.
Yes.
Okay.
So actually, we didn't find it, but actually, Takeuchi-san pointed out this is too over conditioning. So we understood.
Okay.
Yes. Actually.
Okay. Thank you very much. Yeah.
So any other questions? So if no, it's almost time. So thank you for presentation.
Thank you very much.